Okay, so talk will be starting now. No, there we go. So for context, the reason I'm giving this talk is that starting next week we'll be, instead of watching ergodic theory lectures, now watching algebraic geometry lectures. And the lecture series we'll be following will be considering algebraic geometry from a modern point of view of so-called scheme theory. And historically, there's a kind of more geometric and intuitive way of viewing algebraic geometry and how it came about. Scheme theory is really very purely algebraic. It's kind of a generalization of the classical things of algebraic geometry to a more general context. The schemes are so-called rings glued together topologically. And I'll get to what that means today. So that's why we're here. And as a warning, this will be a pretty long talk. As you can see, there's 72 slides. I think it's going to be around 2 hours, maybe somewhere in that vicinity. It's a little hard to tell. There will be a recording. I'm recording right now. And so if you miss something while I'm saying it now, you can go back and see it in the recording. So let's get started. First, let me show you what we'll talk about. I'll start off with talking about just kind of the notion of rings, the whole subject matter of commutative algebra, which is what this is about. So I'll talk about rings and subrings, then various examples of rings, such as products and direct sums of rings. And then I'll talk about various important kinds of rings, especially commutative rings, domains, and fields. Those are all very central things to algebraic geometry and the lectures we'll be seeing. I'll then move on to talking about so-called ideals and quotients of rings. So these things, they're also very central. I'll say something about this now. The way one does algebraic geometry, the whole geometry one gives a ring comes from its ideal structure. So really, these things are kind of the geometric part of rings. So it's very useful for what we'll be doing to consider this. And then I want to, this is kind of not pure commutative algebra, but I want to give kind of insight into the perspective on algebraic geometry we'll be taking by considering something which is kind of in the spirit of algebraic geometry, but with just classical analytical things. So you can see function spaces and see omega here, but don't worry if you're not familiar with any topology or anything like that. I'll make it quite intuitive. I'll try. I just want to give kind of a sense of what we'll be doing in the setting of algebraic geometry with polynomials later, in a kind of more familiar setting. So you kind of don't get lost once we abstract away to this more general setting, and not be in this talk, but then in the lectures of algebraic geometry. And as said, yeah, we're going to replace continuous functions with polynomials. And so lastly, I'll have to talk about polynomials, which is kind of the algebraic way of thinking of functions, and which is going to give us all of the geometry. We'll associate ideals to the polynomials and then look at the geometry that arises. So that's what I'm going to talk about. So if you at any point have any questions or anything else you want to say, feel free to interrupt me or ping me in chat. I'll try to check Discord every now and then to see if there are any questions or anything like that. And then let's get started. So then first I'll talk about rings and subrings. And now what the whole point of a ring is to kind of abstract the structure one has in the usual setting of elementary algebra and things like the integers and the real numbers. So we can add, subtract, and multiply integers or many other things such as rational numbers and real numbers. And well, one thing one commonly does in mathematics, one sees substructure and kind of tries to abstract it away into a notion that we can consider more abstractly and perhaps apply in more settings. So when doing this with the structure of the integers, we get the notion of a ring. And so what we do, we on the set define, so a ring is going to consist of specifying a set and then binary operations for addition and multiplication on the set and a unary operation on the set, minus, so to say, and then two elements of the set 0 and 1. So essentially what we're doing, we have all of these things in the integers, so like the rationals, we have addition, multiplication, additive inverse taking, 0 and 1. And now we're saying, let's say we have just some abstract set and we have all of these things again. And of course, if we just have them, that doesn't mean much. Just have arbitrary things. So we want to impose some conditions, and the conditions one commonly imposes the following. So it might look like a bunch of conditions, but actually if you look at them, they're very kind of intuitive things about the integers, things we all know. So for example, we know that addition and multiplication is associative. So this is the first condition where we can kind of reparenthesize. We know that 0 and 1 act as sort of neutral elements, it's called. So if we add 0 multiplied by 1, nothing happens. Now again, this looks very obvious, But let me remind you here, 0 and 1, they're just some arbitrary things, some elements of a set. Could be anything. They don't have to be integers. They could be matrices, or they could be functions, could be anything. So we're kind of characterizing what it means to be 0 and what it means to be 1, and specifically this. However, we have that additive inverse taking kind of does exactly that. It gives you an additive inverse in the sense that if we add a number to its additive inverse, we get 0. And we also impose commutativity of addition. Note, we do not impose commutativity of multiplication. So commutativity refers to the fact that if I first take A and 10 add B, or take B and 10 add A, I get the same result. And that's something we impose on addition, but not on multiplication. And there's good reason for that. We'll see a great deal of examples later. Just that. And note that the only thing linking addition and multiplication here are the bottom right two properties called distributivity, left and right distributivity, where one says that if one multiplies a sum by an element, it's the same thing as adding the products. So this is, if we do not impose this condition when defining a ring, we have no connection between addition and multiplication. We kind of have two separate structures. So just really a very key property of rings. Yes, let me recall, in case it's kind of going very quickly, what binary operations and unary operations are at all. So a binary operation on a set is just something which takes two elements of the set in some order as an element and gives you another element of the set. So it's kind of how we can combine elements. So formally, I've written this out here as a function x times x to x. So one can do this with any amount of elements, and then as n-ary operations. Here we only concern ourselves with binary and unary operations, because that's what we have in the integers. We have addition, multiplication, binary operations, and we have additive inverse taking, a unary operation. So immediately we get some classical examples. The usual rings one knows has the integers, the rationals, the reals, and the complex numbers. These are all rings that we know from everyday life, kind of in, well, literally everyday life, going about your day, adding numbers, well, grocery shopping or multiplying them. And one gets ring structure because we've abstracted the notion of addition, multiplication, subtraction, etc. from the integers to an arbitrary setting. Of course, the integers themselves are going to be an example. So as plus times minus 0 and 1, we just take the usual things, and then we get rings. So that's one very important example. And before giving more examples, something useful to note is that actually it suffices to give a ring to only specify the addition and multiplication, as long as they satisfy the properties we require, and so they also admit some additive inverse 0 and 1, then the additive inverse taking 0 and 1 are going to be unique. So specifically the statement is the following: if I have some set R and then ring structures plus times minus 0 and 1 and plus times minus prime, 0 prime, and 1 prime, then necessarily minus is minus prime and 0 is 0 prime, 1 is 1 prime. So once we know addition and multiplication, we know everything else about the ring. So often you'll see me later in the talk give definitions of rings, and I'll only specify addition and multiplication. I'm doing this for brevity because you can deduce what the additive inverse taking 0 and 1 have to be. So why is this true? It's kind of a nice illustrative calculation, what one can do in rings. So first you can note that if we have that the addition is the same for 0 and 0 prime, because the neutral elements, we get that, well, 0 is 0 plus the neutral element in addition 0 prime. So 0 is 0 plus 0 prime, but also 0 plus 0 prime is 0 prime, because 0 is the neutral element in addition also. So hence 0 is 0 prime. Then similarly for multiplication, I get 1 as 1 prime. So now we have that 0 and 1 don't depend or are unique. And lastly, for additive inverse taking, using the fact that 0 is 0 prime, we know that if we add to x negative x, or add to x negative prime x, we get 0 and 0 prime respectively, but these are equal. So we have that x plus minus x is x plus minus prime x. So now we have this equality. And what you can do in any ring, we've specified we can take additive inverses and they behave as one would wish. So we can simply subtract x from the left, so add negative x on the left, and we get that, is it a typo? No, that's correct. Negative x is negative x plus 0, so negative x plus x minus x. But also, we have by the previous that it's the same thing as negative x plus x minus prime x. We've just simply subtracted x. It's just negative prime x. So we simply subtract x on both sides, and you get negative x is negative prime x. And thus we've shown that it suffices to exhibit addition and multiplication. You get the whole structure of a ring. Okay, but this is just kind of a general abstract remark about rings, that it suffices to give only a part of the structure, and the rest of the structure follows, if it can, uniquely. And this is kind of nicely illustrative of the sort of things one can do in rings, very kind of down to earth computational things. You can add, you can subtract, etc. I mean, that's in the definition. So we can also note that some other usual properties hold. For example, if we multiply an element of a ring by 0, we get it at 0. So to see that, if we multiply x by 0, it's the same thing as multiplying x by 0 plus 0, which is by distributivity the same thing as multiplying x by 0 and adding x times 0. And then we just subtract x times 0, and we get the 0 is x times 0. So we get that multiplying by 0 is 0. And okay, I've written this on the right, but you can do the same argument on the left to see that 0 times x is 0 as well. Now, similarly, we can show that multiplying by -1 is the same thing as taking additive inverses. Something, I mean, you take this for granted in the integers, but we've only given the properties we required above in a general range, we would have to show that this property follows. I mean, for example, commutativity of multiplication, which you know from the integers, does not follow from the properties we've required. So it's kind of something to be careful about. As you work with rings, you familiarize yourself with what properties follow and what don't. So this is one property that follows. And okay, let's just get familiar how to compute in rings. See why x times -1 is negative x in every ring. So we know that x times -1 plus x times 1 is the same thing by distributivity as x times -1 plus 1. So x times 0, and that's 0 as we've seen before. So now we know that x times -1 plus x is 0, because x times 1 is 0. And then we just subtract x and we get the desired result. So note, in both of these things, we've used distributivity of multiplication over addition, because both claims kind of combine multiplication and addition. Because when we multiply by 0, 0 is kind of an additive thing, multiplication is a multiplicative thing, so we need to use distributivity here. If we do not impose distributivity in our definition of a ring, which is it wouldn't be a ring, but also these properties would not follow. Okay, so these are just very general remarks about how to compute within rings. You can do most of the things you're familiar with in the integers. Well, again, you have to kind of familiarize yourself with what you can do and you cannot, but just these, for example, follow these things. So let's look at some more examples. Actually, first, something that isn't an example. The natural numbers, again, we have addition, multiplication, 0 and 1. Well, okay, depends on your convention, but let's say the natural numbers contains 0. But they do not form a ring with these, with multiplication and addition as usual, these binary operations, because there is no possibility of defining an additive inverse. If you were to define an additive inverse operation, which takes a natural number and gives you its so-called, so to say, negative number, we would have to have something like -1. And that would be a number which added to 1 is 0, but there's no such natural number. So we cannot extend natural numbers to a ring in this way. So that's an example of something which is usual but not a ring. In a ring, we require to have negatives. So yeah, actually, sorry. Before we get to examples, there's some more things that would be nice to see before, just to be able to give more examples. Namely, the notion of a subring, and it's kind of by analogy the same thing as a subset, but now in the context of rings. And we require that things behave kind of ring-wise well, what concerns subrings. So for that, note that in our examples with the usual rings, kind of the day-to-day rings, Z, Q, R, and C, Q kind of sits inside of R, and addition inside Q is the same thing as addition inside R, at least addition of rational numbers inside R. And the same thing for Z and Q. So you kind of have ring extensions, or conversely subrings. And the definition one has is the following. If you have a ring R, a subset S of R is a subring if these properties are satisfied. If S contains 0, 1, contains products of its elements, subs of its elements, and additive inverses of its elements. Okay, it's just a list of conditions, but essentially what this is saying, we are requiring that when we try to view S as a ring by the operations of R, it makes sense. So we want to define an addition on S to make it a ring. And for that, we need to require, if you want it to be the same thing as the addition on R, that, well, the addition of two elements of S is an element of S. And the same thing for multiplication and additive inverse taking, and we also want 0 and 1. And so when we have a subring, it is a ring in its own power. If you have a subring of a ring, by definition, it's just a subset, but we can also view it as a ring. So this gives a very useful way of constructing rings. Namely, you can just take subrings of rings. And for that, one can do something called generation of subrings. And to see that, one first needs to remark this little lemma. And it asserts that if you take any collection of subrings of a ring. So you have some fixed ring R, and then for every element of some index set, a subring Si of R. So for every I the index. If you take the intersection of all of the subrings, so take an arbitrary intersection of subrings, it's going to be a subring again. Now, this is kind of technical thing at first sight, but really it's a very intuitive statement. If you think about it, 0 is contained in this intersection because it's contained in every of the subrings. 1 is contained in the section also because it's contained in every of the subrings Si. So well, I'm verifying that the intersection is a subring. And to see that, I'm verifying that it contains 0, 1 is close to the additive inverse taking, addition, and multiplication. And so it contains 0 because 0 is an Si for every I, because Si is a subring. And similarly, 1 is an Si for every I, because Si is a subring. And so because it's in all of the SIs, it's in the section. So 0 and 1 I in the section. And similarly with addition and multiplication, if I have A in the section and B in the section, if you take A plus B, well, A is an Si and B is an Si for every I, because they're in the intersection. And so the sum is in the intersection. And similarly with the product, and similarly with additive inverse taking. So this lemma just follows like that. And it's a very kind of general thing. This lemma actually generalizes to beyond subrings, to any algebraic structures, and actually to things like topological spaces. It's a very powerful and useful thing, and it allows you to do something called a generation. So what one can do, we have a ring, some ring R, and some subset S of R. S needn't be a subring, just some subset. Usually when one uses notation, S is a subring, but it doesn't have to be. And then we have some elements, A1 through AN of R. What one can do, one can associate a subring to S, A1, and AN by just taking the smallest subring that contains all of them. And it exists by the above lemma, because we can take the intersection of all of the subrings of our ring R, which contain S and contain A1 through AN. And this intersection, it makes sense. So for an intersection to make sense, it needs to have at least one element we're intersecting, at least one set we're intersecting. There's no such thing as an empty intersection, unless, oh, okay, one can kind of make it make sense, but really, in classical set theoretic terms, there's no such thing as an empty intersection, so an intersection of an empty collection of things. You need at least one thing we're intersecting, and this is guaranteed here by just noticing that the whole ring R is a subring of itself, which contains S and A1 through AN. So if you take the intersection of all of them, all of the subrings of R which contain S and A1 for AN, we get a subring, and it's kind of the smallest subring containing S and A1 for AN, also smallest in order theoretic sense. And this already gives a very large variety of examples you can look at. So he's just saying that it's well defined because there is one such subring. So for example, here's an interesting ring that you might have never thought about. And maybe it looks kind of silly at first, but actually it has a lot of number theoretic application. So it's called the Gaussian integers, and they're Gaussian because Gauss considered them. He didn't call them rings at the time. The term ring, I believe, goes back to Hilbert. Kind of consideration of abstract rings started somewhere in the mid-19th century, or maybe a little earlier. They just weren't called rings at the time, kind of a somewhat different object. In a sense, it's kind of a little bit funny. There's this other notion of group. I'm not going to get into groups much into Stalk, but rings kind of predate groups somewhat, even though they are kind of more specified. They have more structure, but they're also more natural in a sense because the structure of a ring, one sees in the integers and the rationals, while the structure of a group is a more abstract thing. But okay, let's come back to the Gaussian integers. If we take in the complex numbers the subset of the integers, and we take I, then we can generate the subring by the integers and I. So I is the complex units going to -1. And we get, as a result, the subring of the complex numbers consisting of all of the numbers of the form a plus bi, with a and b in integers. So it's kind of, if you picture the complex plane, there's going to be a lattice grid, kind of z squared if you want. And this is a ring. You can multiply, you can add. It actually has very interesting properties. And we can construct, for example, this ring by this generation process. Something similar you can do if we don't go to the whole extent of the complex numbers and just say the rationals. To the integers, you can adjoin 1/2. And so we are taking the smallest subring of the rationals, which contains the integers, but also 1/2. Now it's a subring, so it has to contain 1/4 because it's 1/2 times 1/2, and 1/8, 1/2 times 1/2 times 1/2, etc. And it turns out that if we do this generation, we get precisely the subring of all numbers of the form a over 2 to the n, a and n integers. And this subring of the rationals is known as the dyadic integers. Do not confuse them with the two-adic integers. That's something else, and that's to do with p-adic analysis. That's just kind of unfortunate terminology. So that's another example. So another example, this is not an example of subring generation, but it's a very good ring to know. It's the quaternions. And okay, this looks like a mess, but actually it's a pretty intuitive concept. It's a sort of generalization of the complex numbers in a sense by the Cayley-Dixon construction, but that's a different topic for another day. What one does, instead of adjoining to the real numbers just one element I to get the complex numbers, we take I, j, and k. And essentially, we say that elements of the quaternions are kind of just formal sums. So by formal, I just mean it's the same thing as a for tuple. We just have the data of each of the summands in a formal way put together. So a plus bi plus cj plus dk, the a, b, c, d are real numbers. And then we add them in the intuitive way. We just kind of add the corresponding summands, the factors of the summands. And we multiply them, and now this looks like a mess, but actually we just, in a sense, applying distributivity and requiring that I squared is -1, j squared is -1, k squared is -1, I times j is k, j times k is I, and k times I is j. So it's kind of this interesting ring, and one good thing, or maybe bad thing about the ring is it's not commutative. So this is an example of first and the stock example of a non-commutative ring, a ring where multiplication is not commutative. So recall commutativity referred to doing an operation A operation B or B operation A resulting in the same thing. So in this ring of the quaternions, I times j is k, but j times I is -k. So it's a non-commutative ring. And inside of this ring, despite its non-commutativity, just set the complex numbers. We just say C and D are 0, the J and K components of a quaternion number. And we get the commutative ring, the complex numbers. In particular, in the complex numbers, we also have the real numbers. So we get the real numbers as subring and the rationals into integers. So there's kind of a very big ring. There's a lot of things. But later in the talk, we'll see actually a lot larger rings. But yeah, this is a good ring to know. Now, the next big family of examples of rings are products and direct sums. And these might seem like kind of peculiar constructions, but they actually are quite useful for many things we'll see. So first recall that if you have some family of sets, so some index set I, and then for every element of I, a set Ri, so here we have rings, but for now let's just say they are sets. The Cartesian product is a set whose elements are functions from I to the union of all of the Ri, which map each index lowercase I to an element of Ri. So essentially, we are picking out for every element of the index set an element of the corresponding set Ri, where I is our index. And if these things are rings, then this Cartesian product actually becomes a ring itself. Again, it suffices to specify addition and multiplication, and then there's a unique possible ring structure. One can prove that in this case. And what we do, we just say that the sum of A and B, if they are elements of our product, is the unique element whose ith coordinate for I in our index set, the sum of the ith coordinate of A and the ith coordinate of B. So again, the ith coordinate is just the element we get in the ith ring. And the same thing we do with the product. And so we get this big product ring. So this is already an example of kind of a larger ring. If I take an infinite product of R with itself, it's a very large ring. It doesn't contain the quaternions, but it's very large. So a product of commutative rings is going to be commutative because the component-wise multiplication is going to commute. So we get these big rings, and some notation to know if all of the Ri's are the same, some ring R, then we just write R to the power of I. And in the finite case, we just use a cross. So above, I've considered the possibility of a big infinite product, but we can actually just take a product of two things, and I mean, it's the same thing as like in the Euclidean plane, R2, we just take ordered pairs. These functions from the index set to the union are just a generalization of ordered pairs. So if it's confusing, kind of just think about them as large ordered pairs, and instead of having a first entry, a second entry, we just have an ith entry for every I in the index set. So let's just look at some computation into ring Z times Q. We have in the elements 1, 5 and 2, -3 halves. So now in the first coordinate, we enter integers, in the second is rationals. So while 2, -3 halves is an element, -3 halves 2 is not, because -3 halves is not an integer. But we have the element 2, -3 half, and then we can add them, and we get 3, 7 halves if you add 1, 5 to 2, -3 half. And similarly, we can multiply them. We can have these computations. So what one does, one just adds and multiplies component-wise. And that's the same thing as above, except above one allowed for the possibility of having an infinite index set. Instead of just having the first entry and the second entry, one has an ith entry for every element I of our index set. So within the products of rings, there are kind of a smaller version of products called direct sums. And when one considers a direct sum, all one does, so again, we have a family of rings indexed by some index at I. One considers the elements of the product ring of the Ri's over I and I, which have as their components 0 for all but finally many of our elements of I. So this is kind of a way of combining rings in a somewhat smaller fashion. Now, okay, this is kind of, I'm not going to talk about direct sums too much, but it's good to note that direct sums are essentially the same thing as products, except one's required that all but finally many of the coordinates are 0. So notice that if you have just finite, if the index set I is finite, there's no difference between direct sums and products. But if it's infinite, for example, the direct sum from 1 to infinity, so a countable direct sum of the integers is countable, well, a countable direct product of the integers, direct power, is not. It's uncountable. It's a good exercise of elementary set theory. So yeah, notice I'm calling these direct products and direct sums. So I might have not written above that the product of rings is called the direct product, but yes, one refers to it as the direct product, or simply product. Direct is a kind of general term one uses in any so-called category, but we don't have to get into that. Okay, so we've seen kind of the main ways of constructing rings. We can take subrings and generate things, and we can take products and direct sums. I will see some more examples later. But now, something we can ask about the rings we get is some properties of them. So for example, yes, commutativity of multiplication. I said the quaternions, they're not commutative. We can think about examples of rings which are commutative. But another example that isn't commutative is the following. If you have some ring R, any ring, and some natural number n, we can form n by n matrices over R. And all that means is basically we're forming kind of n by n tables of elements of R. Same thing as taking functions from 1 through n squared to R. So for any two elements of 1 through n, if you have 1 and 7, if n is greater or equal to 7, we have the 1/7 entry. These are matrices. And so we take all of these matrices, and the entries in the matrix are elements of a ring R. And one takes, for example, this matrix called 0, this matrix called 1. Then one can define the ring structure on this by defining addition to be just like in the product ring, component-wise. But multiplication, one defines with this peculiar formula you might have seen in school. You kind of take the columns of the right matrix and then you scale and multiply them by the rows of the left matrix. And okay, I'm not going to go into too much into why that is this way one defines multiplication, but this is a matter of linear algebra. Um, and the reason one has this peculiar formula for multiplication is because essentially what one attempts to do with these matrices, when one used in this way, is to represent certain functions. And then one composes the functions when one multiplies the matrices. Again, this is linear algebra. You can find this in any linear algebra book, okay, any good linear algebra book, and any good linear algebra class. But indeed, what one gets, no matter which ring one starts in, long as there's this one peculiar condition that 0 is not equal to 1 in the ring, like there's a non-commutative ring. Just notice that this might seem absurd, but it is possible that in our ring 0 equals to 1. We have not required as part of our definition that they are distinct. We just said that there are some elements. Again, this kind of shows the abstractness of what we're considering. We can take any set R, any 0 and 1 in R, and just long as they satisfy our desired conditions, we get a ring. So yes, notice that 0, 1, plus, times, they're just symbols. They don't represent the usual addition, multiplication, 0 and 1 into integers, the real numbers. They're an abstraction of that notion. But let's turn back to the matrices. Why is the ring of 2 by 2 matrices over any non-zero ring R, so a ring is non-zero if 0 is not equal to 1, a non-commutative? Well, we can simply take these two matrices, and then if we write 2 instead of 1 plus 1, again, this seems kind of silly, but remember, we haven't defined what 2 means in any ring. We just said we have 0 and 1. We have also addition, so we can say that 2 is 1 plus 1. So when we compute the product of A and B, one gets this matrix on the left, 2, 1, 1, 1. And on the right, if you do B times A, we get 1, 1, 2. And they are not the same matrix because one has the left top entry is different from the right. The left top entry of the left matrix is different from the left top entry of the right matrix because 2 is not equal to 1. And how do we know that 2 is not equal to 1? Again, it sounds silly, but we have to verify that in our abstract ring. Well, we know that because 0 is not equal to 1. Because if 2 were equal to 1, we can subtract 1 on both sides and get the 0 is equal to 1. So this is kind of why all of these rings turn out to be non-commutative. And essentially the same reason why function composition is non-commutative. Because this is viewing matrices in this way does. That's just a very famous, important example of a ring that's non-commutative. So yes, rings where 0 equals 1 are called the zero ring, and they're called d0 ring because essentially in any ring where 0 equals 1, every element is 0. So in a sense, it's all the same ring. We'll come back to that later in the second part of the talk. They're also called isomorphic rings. And the reason is if 0 equals 1, then for any element a of our ring, a times 1 is a, but a times 1 is also a times 0 because 1 equals 0. So a times 0 is 0, that means that a is 0. So we have only one element 0, we get the 0. Okay, notice as well that matrix rings, if you take larger than 2 by 2 matrices in a non-zero ring, also are non-commutative. Our above example can be just simply extended by putting 1 on the diagonal, and everything works out to be the same. With constant multiplication, we get essentially, yes, 2 different matrices when we multiply a times b and b times a. So yes, a commutative ring is one where multiplication is commutative. That's one large important family of rings. And actually, in algebraic geometry, because non-commutative rings are kind of messy to work with, we essentially almost always restrict ourselves to working with commutative rings when we view them geometrically. So sometimes non-commutative rings might come up, say matrices, but the geometric rings, so to say, are the commutative ones. At least what concerns how one usually views things, and what we'll be doing in the algebraic geometry lectures. Okay, so the integers are commutative, rationals, reals, and complex numbers are commutative. So here are some more examples. And any subring of a commutative ring is commutative. One more example of a property that one might consider is that of being a domain, integral domain. So actually most people, I think, say integral domain. There's also the way of saying it as an entire ring. I think that's kind of more British. But I personally prefer calling them domains, just it's shorter than integral domain. And the condition one puts on a commutative ring to be an integral domain is that, first of all, it's non-zero, so 0 is not equal to 1. And second of all, if I take a product of non-zero elements, it's also going to be non-zero. These are kind of the 2 properties one requires. And notice also okay, so 2 properties, but we've defined this for commutative rings. So one defines a domain to be commutative. Okay, so also notice that a subring of a domain, subdomain, so to say, is a domain itself. So yes, that's why it's a subdomain. Because, well, if 0 is not equal to 1 in our domain, and we take the subring that we are considering, well, we have 0 and 1 in the subring, and they are the 0 and 1 of the subring, and they are not the same because they're not the same in the ring we started with, so they're not the same. And similarly, we have the same thing for multiplication. If a product is 0, then one of the factors is 0 in our top ring, so also in our subring. So subrings of domains are domains, the same thing. Same way that subrings of commutative rings are commutative. So an example of when we do not get a domain is if we take any product of rings, as long as there are at least 2 rings and they're non-zero, we can simply take 2 different indices, let's say I and j, and writing ES for the element of our product where all of the coordinates are 0 except the S. We have that EI and EJ are both non-zero because, well, the ith coordinate of EI is not 0, but of 0 it would be 0, and of EJ is not 0, of 0 it would be 0. So maybe I didn't notice this earlier when defining product rings, but it turns out that in the product ring, 0 is the element whose all coordinates are 0, and 1 is the element whose all coordinates are 1, simply because we add and multiply component-wise. So okay, turning back to this, we have that EI and EJ are non-zero, but the product is 0. So maybe it's intuitive to think about this in the case of when we take, say, the integers multiplied by themselves, we have as I and j, say 1 and 2, then 1, 0, E1 times 0, 1, E2 is 1 times 0, 0 times 1, 0, 0. But they're both non-zero. And this is kind of an abstraction of this argument. And something very interesting one can do, if one takes this very big product, one multiplies r with itself for every real number one time. Well, maybe that's not quite the right saying it, quite the right way of saying it, but one takes a power of the real numbers, and as our indexing said, we take the real numbers again, then the ring one gets is essentially the ring of all functions from R to R. The reason for that is an element of this power ring, product ring where all of the rings are the same, is a choice of every index, which is here a real number. So essentially a function is from R to R. Again, as we've defined Cartesian products, the elements of the Cartesian products are functions from our index into the union, but here the union is just R. So yeah, we're just looking at functions from R to R. So this way, one can view all the functions from R to R as a ring, and this will be actually important later. And we can see, well, beta above lemma, because the real numbers have at least two elements and aren't zero, not the zero ring. This is not a domain. But one can very visually see this in this case, because we can consider two functions, a and b, and say that they are supported in -2, -1, and 1, 2 respectively. So what this means is they're, so let's also assume they're non-zero functions, but they are zero outside -2, -1, the interval, and 1, 2. So we kind of have this graph. For example, I mean, I've just picked some examples. So A would be the blue one, B would be the orange one. And when we multiply them, well, we multiply them value by value. So we get a new function, a times b from R to R, and say the value at 2 would be the value of a times 2 times the value of b times 2. Well, the value of a times 2 is 0, value of b at 2 is 1, so we get 0 times 1, so we get 0. And you kind of see, no matter where on the x-axis in our graph we take the horizontal axis, we take an index, 1 of a or b is 0 there, so when we multiply we get 0. So despite a and b being non-zero, the product is 0, so this is not a domain. Yes. Okay, and lastly, further very important family of rings is that of fields. And a field is something where we can divide. Notice in our definition of ring, we require that one can add, subtract, multiply, have 0 and 1, but we did not require division. Otherwise, the integers would not be a ring, because we cannot divide into integers. We can divide to get a rational number, but not to get an integer number, but we want to work entirely without a ring. So a commutative ring that's non-zero is called a field. If for every element lambda of it, there's some element lambda inverse, which is called lambda inverse, such that lambda times lambda inverse is 1. And in fact, it makes sense to call it lambda inverse because it's unique. If lambda alpha is lambda beta, then by distributivity, lambda alpha minus beta is 0. Then alpha minus beta is alpha times lambda, because that's 1, times alpha minus beta. But alpha times lambda times alpha minus beta is alpha times lambda times alpha minus beta by associativity, and that's alpha times 0, so it's 0. So we get alpha minus beta is 0, and so alpha is equal to beta. So we get if multiplicative inverses exist, they are unique. So the rational numbers are a field, the reals and the complex numbers too, but the integers are not a set because, well, if we had a field structure there, if we had a way of taking multiplicative inverses of non-zero elements, then there would be a non-zero element to inverse of 2, but there's no such element to inverse of 2, such that the product of them is 1. 2 times x equals 1 has no solutions in the integers, so the integers cannot be viewed as a field in the usual ring structure. Okay, so here's a nice, I don't know, calling it nice, maybe giving too much credit, but here's a visualization of the families of rings we've considered. So in the red rectangle, we have just the class of all rings visualized as this filled in rectangle and the points in rectangle rings. So we have the 2x2 matrices with the integers say, and we have the quotients. And then we have within it the commutative rings, within the big rectangle of all rings. Then we have things like products of commutative rings, z times q, or powers r to the power of r. Then we have domains, like the Gaussian integers or the integers, and then we have fields, u, c, etc. Okay, so that will be the end of part 1 of my talk. Does anybody have any examples? Any questions? Let's give it a few seconds. It's fine if it's something you would think is a stupid question. I mean, I think if you have this question, maybe somebody else might as well. So it doesn't hurt. Doesn't hurt to ask. So somebody's asking why. So your question. Mhm. Oh, I see. Yes, so the question is for the recording, because what people are saying in the call is not being recorded, just what I'm saying. Somebody's asking. No, it's all good. Somebody's asking why in our definition of a ring. So let's. Okay, I'll have to scroll a lot, but Yeah, here, why we additionally require a unary operation minus as part of a ring structure when we could have just said that there exists a minus and under addition it satisfies these properties. I mean, it's kind of a matter of preference. One could either define a ring by saying that one has the structure of a set plus times and minus, or by saying we have a structure of a set R and then plus and times and there exists a minus. And as we've seen on the very next slide here, it doesn't matter which way one does it. Either way, one gets the same thing because if there exists one, it's unique. So really, it's a matter of preference. And the reason I put it here because I think this illustrates the things one needs in a ring. I mean, one explicitly needs an additive inverse taking in a ring. And if one just says that there exists one, well, a priori there might exist multiple. One has to think about this. Again, it's a matter of preference. The reason I put it like that here is just so it's clear that in the ring one has addition, multiplication, additive inverse taking. Okay, I hope this answers the question. I mean, again, it's kind of a matter of preference. Does it? Is the question cleared up? Well, I'm talking both to the camera and the audience. No, but is it fine? Okay, good, good. Any other questions? Yeah, okay, so somebody is asking whether when one considers functions and their composition, when one gets a ring. So let me be more clear. So I mentioned this here. I mentioned this here. One can think of matrices, n by n matrices with entries in the ring R as functions Rn to Rn. This is a standard linear algebraic way of doing this. Well, actually, one has to specify two bases, but it doesn't matter. We can just take the standard basis. And then matrix multiplication corresponds to composition of these functions. And this ring one gets if one instead considers linear functions Rn to Rn and considers as multiplication per composition. This is actually something one can commonly do. One can define multiplication to be composition. And in many contexts, that works just fine. But what this ring we get is 0. That's the question. No, it's not 0 because the ring we get is essentially the same thing as the ring of the matrices. We'll see it's an isomorphic ring. We can think of matrices as linear functions or linear functions as matrices, and it's the same ring basically. So we get essentially again the ring M and R, which is non-zero. I mean, we have 0 on the left, 1 on the right here, and they're different because 0 is not equal to 1. Okay, it's non-zero if the ring we start with is non-zero. Does this clear things up? Yes, if R is non-zero, then for any positive integer n by n matrices over R form a non-zero ring as well, because we have 0 on the left here, 1 on the right here, and the left upper corner entry 0 and 1 are distinct because R is not 0. And this is the same thing as considering functions Rn to Rn which are linear under composition. Okay, good. Any other questions? I mean, I appreciate questions because if the whole point of this is to explain things, so if people get lost, it's kind of the point of this to explain things, and it's kind of my fault for not explaining them clearly enough. But okay, if there are no questions, otherwise I'll move on to the next part of the talk, talking about quotients and ideals, a very important thing, as said, for algebraic geometry. Well, the whole of geometry comes in. So okay. Oh yeah, another question? Mm-hmm. Yeah, no, it's okay. So somebody asked where one can see the slide numbers. The slide numbers in the right lower corner. Yep. Okay. So yes, let's move on to quotients then. So okay, to talk about quotients, we first have to talk about quotients. We talk about quotients of rings. We first have to think about quotients of sets, and that's maybe something you might have not seen before, or maybe you have. But the idea is essentially identifying elements with each other. And for that, one needs the notion of equivalence relations. So let me just recall or remind you what these are. So a binary relation on a set is just a subset of the Cartesian square of it. So what this means is when we specify a binary relation tilde on a set X, we simply specify a set of ordered pairs whose components are in X, which we say that lie in the binary relation. And when A, B lies in the binary relation, we say that the relation relates A to B, right? Kind of A tilde B if tilde is the name of the relation. So this way we can think about kind of what it means to be related in a way under some law of relation. For example, or maybe a silly example, on the set of all humans, we can take the binary relation such that we take all the ordered pairs A, B, such that A is married to B, for example. If we have some well-defined notion of marriage on humans, we get this binary relation. And then we can consider various notions of binary relations, such as reflexivity, simplicity, and transitivity. And they are the following. A binary relation on the set X is transitive if every element is related to itself. It's symmetric if whenever X is related to Y and Y is related to X, both X and Y it's symmetric if X is related to Y implies that Y is related to X. And it's transitive if when X is related to Y and Y related to Z, then X is related to Z. And whenever we have these three properties, reflexivity, simplicity, and transitivity, they kind of give us something which is similar to the notion of similarity or equivalence. Everything is equivalent to itself. If X is equivalent to Y, then Y is equivalent to X. And if X is equivalent to Y, Y is equivalent to Z, then X is equivalent to Z. And so we call binary relations that are reflexive, symmetric, and transitive equivalence relations on sets. So there are many other properties of binary relations one could consider, such as antisymmetry or strictness, in all of what irreflexivity, many other things, connectedness, and one gets things like orders and well, many other things, graph theoretic things. But here we concern ourselves with equivalence relations, because this kind of, so what we'll be doing is kind of dual in a sense, in a category theoretic sense, to inclusion of rings. We'll be doing kind of quotients of rings. Well, okay, maybe that doesn't say much to you, but you'll see what this means in a moment. So let's consider an example of equivalence relation, actually a whole family of examples. Whenever we have sets in X and Y and a function from X to Y, we can get an equivalence relation on X associated to F by saying that X and X prime and X are related or equivalent to this equivalence relation when their value and the F is the same. So for example, if I take the integers as X and as Y we take negative 1, 0, and 1, and we take this function, which is kind of the sign function, not sign as in sinus, but sign as in signature, it maps an integer to negative 1 if it's negative, to 0 if it's 0, and 1 if it's positive. We also get an equivalence relation on the integers. And the way this equivalence relation looks like, then we have that X is related to Y for integer X and Y, whenever they have the same sign, whenever f of X equals f of Y. So whenever they're both negative, both 0, or both positive. So note we get this kind of decomposition of the integers called the partition, and negative integers into the singleton 0, and then the positive integers. And this partition has the property that any two elements of one of these sets, if they're in the same set, they're equivalent, and if they're not, they are not. In particular, these sets are pairwise disjoint, meaning they have no common elements if they're distinct. So this is a general thing one can do. So given a set X and equivalence relation tilde on X and some element P of X, we can define the equivalence class of P under tilde as the set of all elements of XQ which are similar under tilde to P. And one uses this notation, square brackets P underscore tilde. There's also some other notation. Sometimes one omits the tilde if it's clear from context. And one calls P a representative for the equivalence class. And then the quotient set, this is where the quotients come in, of X modulo tilde, is when we take the set of all of the equivalence classes of tilde and X. Essentially what one is intuitively doing, one had some set and one had some equivalence relation. Some things were considered equivalent. But when forms the quotient, one identifies any two equivalent things into one thing, the equivalence class. The equivalence class of A equals the equivalent class of B whenever A and B are equivalent. So essentially, we're just identifying things. This is what we're doing here. If you do this above in our example with the integers and the signature function, then what one gets is one gets three equivalence classes, all of the negative integers, the singleton 0, and the positive integers. And so we've essentially identified the whole of the positive integers into one, the whole of the singleton 0 into the whole of 0 into 1, and the whole of negative integers into 1. You get these three things. So that's what one does. And notice that what one has for these equivalence classes is the same as what one had in one example above. It partitions X, the set of all of equivalence classes. What this means is X can be written as the union of all of the equivalence classes of tilde, where tilde here is any equivalence relation on X. And these equivalence classes, they are pairwise disjoint. If you have two distinct equivalence classes, they cannot intersect, because any element in the intersection would be similar to representatives of both of them, and so by transitivity they'd be equal. You can think about that as kind of standard things, equivalence relations. And yes, they cover all of x, meaning that the union is equal to x because every element of x is contained in its equivalence class, meaning it's in one of these kind of blocks of the partition. Actually, in this way, we can view partitions and equivalence relations the same thing. An equivalence relation uniquely determines a partition by the equivalence classes. And conversely, if you have a partition, you can define an equivalence relation whose equivalence classes are the blocks of the partition, saying that A is similar to B whenever they lie in the same block. So if that's too much, the most important thing here is when one takes a quotient by an equivalence relation, one just identifies all of the similar things. This is what we'll have to do. And what we do next is consider this with rings. This is kind of dual to subrings. Now we get quotient rings. We have to be kind of careful. Because when one considers subrings, then not any subset of the underlying set of a ring. So something I should have mentioned earlier, I say subset of ring sometimes, or element of ring, but a ring is a multitude of data. We have a ring, we have a plus, a times, a 0, a 1. One always means the set in the ring. I mean, maybe that's kind of obvious, but it's good to specify that when one talks of elements of a structure, one always means the elements of the underlying set. And similarly, functions out of a structure and subsets, etc. It's the same with topological spaces or any other things like graphs. Okay, so yes, when considering subsets of a ring, not all subsets give you subrings. And similarly, when considering quotients by equivalence relations of a ring, not all quotients give you quotient rings. And basically what this means, when we want a quotient ring, ideally we want to define addition and multiplication on the quotient in the following way. We want that the addition of equivalence classes is the equivalence class of addition, and multiplication of equivalence class of multiplication. Now, the reason why I ideally want to do this is because there's really no other obvious way of inducing a ring structure on the quotient. We kind of have to do this. But a problem arises here because in general, we cannot write down the equation equivalence class of R plus equivalence class of S equals equivalence class of R plus S as a definition of plus, because the equivalence class of R plus S depends not only on the equivalence class of R and the equivalence class of S, but on R and S, the representatives in general. We have to check so-called well-definedness. And well, our definition, one that one often takes, is that a congruence is an equivalence relation whenever this is well-defined. So whenever, no matter which two representatives of two equivalent classes I take, their sum is going to be in the same equivalence class. It's going to be similar. I'll write out what it means in a second. And this is a notion of, this notion of congruence is something you might not find actually in many commutative algebra books, because usually one immediately jumps ahead to the notion of ideal, which I'll get to in a second. But this is kind of, I feel like, a more intuitive way of viewing what the point of ideals is. Because usually when it's going to replace the congruences by ideals, as we'll get to in a moment, but it might seem artificial if one just immediately starts with ideals, you wish to consider quotients after all. So the proper notion is equivalence relations. So these equivalence relations that behave well, giving us quotient rings, are called congruences. So whenever we have an equivalence relation R such that these two equations are well-defined, give us well-defined operations in the quotient ring, one can check that these two operations in the quotient ring give us a ring structure. It's something to check. It's like a little lemma. I'm not going to go for it. You can check it if you're interested, or find it in any commutative algebra book, though in slightly different phrasing usually. So yes, one defines then the quotient ring of R modulo congruence whenever this is the case. And some things to note is that the 0 in our quotient ring is the equivalence class of 0. The reason for that simply is if you take the equivalence class of A plus the equivalence class of 0, so any element of the quotient ring plus 0 in this way, we get the equivalence class of A plus 0 by our definition, and that's the equivalence class of A. So this acts as a neutral element. Same thing for multiplication with 1. And also with additive inverse taking, we also kind of bring in the minus into our equivalence class brackets. So let's think about what it means for an equivalence relation to be a congruence. Specifically, what it means is these two conditions I wrote down below. If we have that R is similar to R prime and S is similar to S prime, some elements of the ring, we want that R plus S is similar to R prime plus S prime. The reason we want this is because what we want is that if we add the equivalence class of R to the equivalence class of S, we get some well-defined equivalence class of R plus S. But if this implication were to fail, the equivalence class of R plus S would not merely depend on the equivalence classes of R and S, but also the percentages from the X, as said. So one wishes to require these two conditions, the same thing for multiplication below. This is exactly the same as requiring the condition in the previous slide, and this is what makes an equivalence relation a congruence. So this is what one, this can be took as an alternative definition of a congruence on a ring, and equivalence relation satisfying these two properties. So maybe if the previous one, in terms of well-defined, is a somewhat abstract to look at, this is a very concrete way of writing it down. So this also allows to look at some examples. For example, we can take on the integers the equivalence relation, which takes the function of parity. It sends an integer to its parity. Let's say either 0 or 1, 0 if it's even, 1 if it's odd. And then we get an induced equivalence relation. So we have that x and y related, and there's equivalence relation tilde on the integers whenever they have the same parity. So in other words, whenever x minus y is even. Because if x and y are both even, then x minus y is even. If x and y are both odd, then x minus y is even. But if one of x is odd and one of x and y is odd, but the other is even, then x minus 1 is odd. So this is kind of the same way of saying that x and y have the same parity to say that x minus 1 is even. So this is a congruence. Now why? Well, we can check with the conditions above. We can explicitly check that on the quotient ring we get well-defined ring structure on the quotient set. If R and R prime and S and S prime are related under this equivalence relation, then R minus R prime and S minus S prime are even. So then the sum, as the sum of two even numbers, R minus R prime plus S minus S prime, which is the same thing as R plus S minus R prime plus S prime, is also even. But this means as much as that R plus S is related to R prime plus S prime, because the difference is even. So this shows that addition is well defined on our quotient set. And one can do the same thing with the multiplication. One has to be kind of more careful in how one derives the fact that the difference is even. One can write it as a sum of multiples of even numbers, as I've done here below. It's kind of a computation. If you're interested in looking at this, you can go with it later yourself. This is also something we'll see more generally later in a greater generality. Okay, so yes, so what one gets is a quotient ring because we have a congruence on a ring. And this quotient ring, its elements, we've identified the integers by the parity. So we've identified all even integers, all odd integers. We have two equivalence classes. And well, we get a addition and multiplication structure on these identified things, on these equivalence classes. And one can write down specific addition multiplication tables. Sometimes people kind of pretentiously call them also Cayley tables, because Cayley was one of the first people in group theory who looked at multiplication tables. But okay, that's getting afield. It looks like this. Now, the way one can derive these is to note that when one computes, say, e plus e, it's the equivalence class of 0 plus the equivalence class of 0, so it's equivalence class of 0 plus 0 is the equivalence class of 0. Or say, O plus O is the equivalence class of 1 plus the equivalence class of 1 is the equivalence class of 1 plus 1. So of 2, so of 0, because 2 is even. So another way of seeing this is that, or reading these tables, is that any even number plus any even number is even, any odd number plus any odd number is even, etc. The same thing multiplication. And the fact that our partition comes from a congruence, so that even and odd partitions kind of in congruence way the integers, is specifically that this makes sense, that no matter which two even numbers one adds, the result is going to be even. It cannot be that for some it's even, for some it's odd. This fact is specifically that tilde here is a congruence of the integers. So note here, as noted above, 0 is the equivalence class of 0, it's the evens, and 1 is the equivalence class of 1, it's the odds. We kind of have a ring, it only has two elements, 0 and 1. And it looks like this. So now another way of thinking about congruences is that means ideals. And the idea here is to note that, well, if you have the congruence tilde on a ring and some elements x and y, well, x is congruent to y precisely when x minus y is congruent to 0. The reason for that is if x is congruent to y, well, also minus y is congruent to minus y. So x plus minus y is congruent to y minus y, so to 0. So in our case here, we have the fact that x minus y is even whenever x minus y minus 0 is even. So whenever x minus y is similar to 0. But indeed here, more generally, we have the following. If you have a ring R and congruences tilde and tilde prime and R, if they have the same equivalence class at 0, so if we know what is similar to 0 on both of them, then and it's the same, then they're equal. So indeed, if you have any congruence kind of hamburger or triple bar on R, if you have that x is under it equivalent to y, it's the same thing as having that x minus y is congruent to 0 under it. Now, the reason for that is what I've just said. If x is congruent to y under our congruence, equivalent to y under our congruence, well, then just subtracting y on both sides, and you can do this because it's congruent, because x is equivalent to y and negative y is equivalent to negative y. So we have that x plus minus y is equivalent to y plus minus y, so to 0. So we get that x minus y is equivalent to 0, what we want to show. Conversely, if we know that x minus y is equivalent to 0, we can add y on both sides and get that x is equivalent to y. So we can really recognize congruences just by knowing what's equivalent to 0. Because we know that if we know what's equivalent to 0, we know when x minus y is equivalent to 0. And then we know when x is equivalent to y. And this motivates the notion of ideals, which is really what one, as I said, usually looks at in commutative algebra and where the geometry comes from. But really, it's kind of a representative for congruences. Not representative in the strict sense, but something one can think of instead of congruences. So an ideal of a ring R is a subset of Ri such that there's some congruence on R such that it's the equivalence class of 0 on this congruence. So one sometimes writes it as this triangle thingy, like less than equal, but then one writes a triangle. And then instead of writing R modulo congruence for the quotient ring, one writes R modulo equivalence class of the congruence at 0, R modulo the ideal of the congruence. And as I've seen above, if the ideals, so the equivalence class at 0 of two congruences is the same, then the congruence is the same. So really ideals are a different way of thinking about congruences here. Yes, I think that's all I want to say here. So in the case of our example above, on the integers, with the congruence, when two elements are similar, when they have the same parity, the equivalence class of 0 is just all the even numbers, and that's an ideal. But the odd numbers, they're not an ideal because there's no congruence whose equivalence class of 0 they are, because any equivalence class of 0 contains 0, because it's the set of all things similar to 0 under some equivalence relation, but 0 is similar to 0 under any equivalence relation by reflexivity. So we already get that not everything can be ideal. It's very useful to think about which subsets are ideals, and there's a very simple characterization, namely the following. So a subset I of a ring R is an ideal whenever the following holds. First of all, it has to contain 0, which is clear because any equivalence class of 0 contains 0, as said before. Also, it has to be closed in the sum. So if A and B are in I, then A plus B is in I. And it has to be closed in the scaling by arbitrary elements of our ring. If A is in I and R is in R, then R times A is in I and A times R is in I. Okay, so kind of where do these conditions come from? It's essentially coming from the properties of 0. Because when we quotient by an ideal, we are viewing the ideal as 0. We are identifying all of it to 0 because it's the equivalence class of 0. So under some equivalence relation, every element of the ideal is equivalent to 0. And so all the properties that 0 has, for example, as absorbing and the multiplication, when we multiply by 0, we get 0, are kind of transferred into ideals. If you have an element of an ideal and multiply it by something, we again get an element of the ideal. In the quotient ring, this is just saying as much that multiplying by any element by 0, we get 0. So let's write this out carefully. There are two implications to show. First of all, if I is an ideal in R, then we have these properties. And conversely, if we have these properties, then I is an ideal of R. If I is an ideal of R, then we can write this as the equivalence class of 0 in the congruence relation on R. Well, because it's the equivalence class of 0, and 0 is similar to 0 by reflexivity, 0 is in I. Now also if A and B are in I, well, because I is the, oh, there's a typo, sorry. It should say 10I equals congruence, the equivalence class of 0, not R equals equivalence class of 0. So sorry for the typo. But yes, if A and B are in I, then because I is the equivalence class of 0, A is similar to 0 and B is similar to 0, but then A plus B is similar to 0 plus 0 because we have a congruence. So A plus B is in I. So then I is close in addition. And by scaling, we have the same thing. If we have A and B in I and R in R, then A is similar to 0 and B is similar to 0. I guess so we just need A. If you have A and I, then A is similar to 0. And we have any element R of R, then R is similar to R. But then R is similar to R, A is similar to 0. Multiplying them together, we get R times A is similar to R times 0 to 0, and on the opposite as well. A times R is similar to 0 times R, which is 0. So we get that R times A and A times R are both similar to 0, so in I. This shows that ideals have these properties. And again, we've basically just replaced an arbitrary element of our ideal by 0 by considering it up to equivalence under tilde. Where tilde is the congruence relation we have. Now, conversely, if we have a set that satisfies all of these things, and we wish to find a congruence such as the equivalence of 0, well, we know what this congruence has to look like. Necessarily, if a congruence induces some ideal I, we have that x is similar to y whenever x minus y is similar to 0. So whenever x minus y is in the ideal I. So this is how we can define a binary relation tilde on R. We say that x is related to y whenever the difference is an element of I. Okay, so there are many things to check. We need to first check this equivalence relation and then check this in congruence. So let's first check this in equivalence relation. If you have elements x, y, and z of R, then x minus x is 0, which is an element of I by the first property, the left upper corner of the block of 4 properties. And so x is similar to x, so we get reflexivity. If x is similar to y, then x minus y by definition is in I. And so multiplying by -1, scaling by -1, by one of the properties above, we get that y minus x is similar to 0. That is an element of I. So we get symmetry. And also we get if x is similar to y and y is similar to z, so x minus y is in I and y minus z is in I, then the sum is an I, again by one of properties. And the sum is x minus z. So we get that x minus z is an I and x is similar to z. So we've checked that this relation we get is an equivalence relation provided we have these properties. And so now we also need to check this the congruence. If we have some r prime and s prime, which are related by our equivalence relation, then by definition, r minus r prime is an I and s minus s prime is an I. So their sum is an I by the property. So r plus s minus r prime plus s prime is an I. Again, it's the same thing as we did earlier with the integers, just in a greater abstraction. And we get that r plus s is similar to r plus s prime. And similarly, the same thing with multiplication. And so we get that this is a congruence, and indeed the equivalence class of 0 under this congruence is everything that has x minus 0 element of I, so everything which is in I. So it's I. So we found the congruence whose equivalence class of 0 is I. So indeed, this uniquely characterizes ideals. So it's kind of a computation, but I think it's very illustrative to go for it because it kind of illustrates the notion, the point of the notion of an ideal. It's everything that's kind of 0 in a way. Everything we can group together into 0, and we still get multiplication, addition, subtraction, everything working well. And once you have that, you can quotient by the ideal by quotienting by a corresponding congruence and get the quotient ring. So something to note is about how the equivalence classes of a quotient ring by an ideal look like. And for that, let's introduce this notation. It's pretty common. And the sets that result via this notation are called cosets. If you have some set A, and some subset of a ring A, and some element x of the ring, then we write x plus a or a plus x for the set of all of the sums. X plus a, where a is an element of a. And in the case when a is I, we call these cosets of I, if I is an ideal. And the reason for that is that these are precisely the equivalence classes of the congruence corresponding to an ideal I. They're all sets of this form. So if we have some ring R, again, and some ideal I of R, the equivalence classes of R modulo I are precisely sets of this form where we replace A with I. So let's prove this. If we have an equivalence class of some element lowercase a in R under the congruence corresponding to I, we've seen what the congruence looks like above. It's the congruence given by x similar to y whenever x minus y is in I. Then we have that if we have an element x in the equivalence class of A, then x is a plus x minus a, which is kind of by properties of rings. But x minus a is an element of I. Why? Because x is similar to a, because it's the equivalent class of a. But then subtracting a, because a is similar to a, we get x minus a is similar to a minus a, so to 0. So we get that x minus a is similar to 0, so it's an element of I. So in particular, we get that x can be written as a plus x minus a, but x minus a is an element of I, so as an element of a plus I. So we've shown that the equivalence class of a is contained in a plus I. Now conversely, if we have something in a plus I, so x can be written as a plus I by I is an element of I, well then x minus a is similar to 0 because it's just I. And consequently, x minus a plus a is similar to 0 plus a. So x is similar to a, and so it's in the equivalence class of a. And then we have that every element of a plus I, capital I, is an element of the equivalence class of a. And we've shown that the equivalence class of a is a plus I. And this shows that the equivalence class is precisely of this form. This is good to know because often people, instead of writing an equivalence class modulo an ideal as the equivalence class brackets a tilde, maybe tilde underscore I, they just write a plus I, like x plus I. And what they mean is just the equivalence class because, well, it is the equivalence class in this notation. So let's look at an example. If you take, again, our example with the integers, and we take the ideal of the even numbers within it, well, then the quotient set, as you've seen, has two elements. It has all of the odd integers and all of the even integers as equivalence classes. And 0 is e, and 1 is o, if e is the evens and o the odds. And one has that e is 0 plus e in our above notation, and o is 1 plus e. And indeed, this is how the equivalent classes look like. They are cosets of I. And so people, when talking about the odd integers as an element of this quotient ring, might write just 1 plus e. So just something to keep in mind when you see 2 plus some ideal, it's just this equivalence class in the quotient ring. Okay. So something good to keep in mind, just like with subrings, we can generate ideals. And for that, we have the same lemma. Again, as mentioned, this lemma is of incredible generality. One can use it in many situations. I'm just giving you specific instances. If we have an intersection of ideals as an ideal, and the reason is the same as why the intersection of subrings of a ring is a subring. If we have some, first of all, zeros in each of the ideals we're intersecting, so it's in the intersection. Also, if we have elements A and B of the intersection, then they are in all of the sets we're intersecting, all of the ideals. And because the things we are intersecting are ideals, also the sums are in the ideals we're intersecting, and so in the intersection. A plus B is in the whole intersection if A and B is in intersection. And similarly, the same thing with scaling. So this is indeed an ideal. And we can do the same trick as we did earlier and generate the smallest ideal containing some subset of a ring. So, oh, well, I just wrote out what I said. But what one can do is the following definition is, given a subset S of R, the notation one uses is these open parentheses S, and this is the ideal generated by S. In conventional terminology, it's the intersection of all of the ideals containing S, which are ideals of R. And it's an ideal by the above lemma, and the intersection is again well defined because we can take the whole ring R. It's an ideal of itself because, well, it's closed under all of the properties. The corresponding congruence identifies everything. The quotient ring is a zero ring. Okay, so this is how one can get a lot of examples of ideals, and it's kind of very useful. Again, this is these things about ideals are going to allow to look at geometric notions in arbitrary commutative rings, and maybe not in this talk, but then in the lectures. So it's very important to familiarize yourself with the generation of ideals, or just all of these notions about ideals. Perhaps congruences are kind of a technical way of thinking about things, but just be comfortable with working with ideals if one wishes to study algebraic geometry, at least in the modern sense. So yes, it's well defined because the whole ring can be took as an ideal in itself that contains S. And one thing to note is how one can characterize ideals generated by a finite subset of R. If you have a finite subset of R, we can note that the ideal generated by it is just the sum of all of the so-called linear combinations of the elements of this finite subset. Actually, this is true for infinite subsets as well, except then one has just pick out finite subcollections and then take linear combinations of those. So a linear combination is this kind of sum when one scales all of the elements of our set and then adds them up. And the scalable elements of our ring. And the scaling is just multiplication. Yes, these kind of products are called linear combinations. You take the set of all of them, you can prove this is exactly the ideal generated by S1 for Sn. So you can check this as a nice exercise, just kind of practice all of your ideal notions I've just introduced. And this is kind of the reason why one uses the notation sometimes, especially in older books, sum from I equals 1 to n RSI, like RS1 plus RS2, etc. plus RSN for the ideal generated by S1 for Sn. In particular, something you'll see very often is the notation S1R or RS1 for the set of all multiples of S1, which is the ideal generated by S1 by the above lemma. And these ideals generated by a single element, are called principal. So essentially what we're doing, we are taking some element of a ring, and we are saying we want to identify it with zero. We put an ideal, and we look at the smallest ideal that achieves it, that contains this element. So kind of the smallest amount of identifications you need to make to identify an element with zero. And ideals of this form are called principal. Okay, it might seem like an abstract definition, but actually there'll be many examples of principal ideals we'll see, and maybe you get a feel for them. So an example of a principal ideal is the ideal 2z. So set of all multiples of 2 in the integers. This is just the even numbers. The ideal we saw earlier, and the congruence we saw earlier corresponds to this ideal, and we get the ring z modulo 2z. So earlier I noticed this ring first z modulo congruence, tilde, but tilde was defined by that x is related to y whenever x minus y is even. And then I noted z modulo e, but e is the set of all even numbers. Now we can rewrite the set as 2z, and this is the most common notation people use. So you very often see people write z modulo 2z, or maybe sometimes z modulo 2, and they mean the ideal generated by 2, or just many notations. But this is something to keep in mind. The ideal denoted, the ring denoted by z modulo 2z is we take the ring z, we take the ideal generated by 2 in z, which happens to be all of the multiples of 2, so 2z, and then we quotient. So we identify 2 with 0, and the way we do this, we take this equivalence relation, x is similar to y whenever x minus y lies in the ideal to z. So whenever x minus y is divisible by 2, multiple of 2 into z. So even. This actually suggests how we can generalize our example from before. We can, instead of taking 2, take any natural number, any integer n, then consider the ideal generated by n, nz, the set of all multiples of n. Then we can say that two elements of the integers are related under this ideal, or the congruence corresponding to this ideal, whenever the difference is divisible by n. And we get the ring z modulo nz. Now, something about the string to note is that it has exactly n elements. The reason for that is so-called Euclidean division. Every integer, if you have some natural number n, let's say, can be, okay, let's say we have, actually for this we need a positive integer n. So 1, 2, 3, etc. We can take this for this remark to hold that it has exactly n elements. If we take some integer and some positive, some integer x and some positive integer n, there's a theorem of elementary number theory which says that we can uniquely write x as qn plus r, where q is some integer and r is an integer which is non-negative and less than n. So kind of perhaps this looks very abstract, but really if you think about it, this is what you would intuitively get if you try doing this. Say we want to, is division with remainder. If you want to divide, if you take as x5 and as n2, we can write 5 as 2 times 2 plus 1. And 1 is our remainder, 1 is between 0 and 1, and we get this. But what we get is that we can write any integer x like qn plus r. Well, and qn is an element of our ideal, so in the quotient it's 0, because we quotient the ideal to be 0. We've identified with 0. So upon identification, we get that x is similar to r. So strictly speaking, we have that x minus r is qn plus r minus r, so qn, which is in the ideal. So x is similar to r, but r is in 0 for n minus 1. So you get that z modular and z has at most n elements, but also it's at least n elements because you can kind of clearly see that any two elements of 0 for n minus 1 are not going to be related by this relation because the difference, unless they're equal, because the difference is a positive number less than n, and it's not divisible by n hence. So what we get from this is that z modular and z is a ring with n elements. So it's actually a very interesting example. We get that there exist rings of any finite cardinality, z modular and z. Actually, for some cardinalities, it's the only rings. Not many, but there aren't many finite rings. In group theory, one often studies finite groups with rings, that's less so the case. It's less interesting. You study finite fields, actually. There's a big theory, it's very useful in computer science. Actually, it's also sometimes useful in algebraic geometry, specifically arithmetic geometry, but that's a different topic. So we have these rings, z modular and z. Again, we take the ideal generated by n and z, set of the multiples, induce the equivalence relation by saying that x is similar to y whenever x minus y is in the ideal n z. So whenever x minus y is divisible by n. And then we take the quotient of the integers by the equivalence relation and we get the quotient ring because it's a congruent, because we start with an ideal. So here's a multiplication table for z modular for z. And here we have our equivalence classes, and I wrote them in this coset notation. So we have our ideal for z, and then I can shift a little bit by some integer, and I can use these representatives 0, 1, 2, and 3, and I get all of the equivalence classes, all of our elements of z modular for z. And this is how they multiply, and I get the same thing we did with multiplying even odd numbers. If I multiply something which is remainder 3 mod z by something which is remainder 3 mod z, I get something remainder 1 mod z. And the reason why this works is precisely what we covered before, because multiplication is well-defined modulo for z, because for z is an ideal, because it's closed under scaling, under addition, and contains 0. So for example, if I take 7, which is 3 modulo 4, and I take 3, which is 3 modulo 4, 3 times 7 is 21, which is 1 modulo 4. It doesn't matter what I start with, always get 1. And this is really what it means to be an ideal, that when we do this multiplication, it makes sense of the cosets. Okay, so this is kind of what these rings look like. It's interesting to look at. Note that this ring, so maybe I didn't say much about the properties of z modular to z, but actually z modular to z turns out to be a field. It's kind of intuitive if you think about it. We have only two elements, 0 and 1. So every non-zero element has a multiplicative inverse because every non-zero element is 1. Also, it's clearly commutative and 0 is not equal to 1. But this is actually not a field. If you notice, 4z plus 2 is non-zero because it's not 4z. And 4z plus 2 times itself is 4z, because anything which is 2 remainder 4 multiplied by itself is 0 remainder 4. So we have two non-zero elements which multiply to 0. So it's not a domain. Not only not a field, not a domain. So it's something interesting to think about. When is z modular and z a field or domain? That's what we get next. Actually, not quite yet, but in a moment we'll get to that. So first, something good to remark is that every ideal of the integers is principal, and in fact can be uniquely written as nz for some natural n. It cannot be uniquely written as nz for an integer n. Principal ideals not have a unique way of being written as an ideal generated by something. For example, the set of all the multiples of 2, the integer multiples of 2, is the same as the set of all the integer multiples of negative 2. And okay, maybe that sounds silly, but in some other rings this turns out to be kind of less trivial. But indeed, if we restrict n to be natural, every ideal of the integers can uniquely be written as the ideal generated by some natural number n, as nz. So let's prove this. This is a kind of fun proof, I think, because it uses some, well, I'm not sure how to argue why it's fun, but actually I find this proof a little fun. So first, let's consider cases. First, if our ideal I contains no positive integers, we can also see that it contains no negative integers. Because if it were to contain some negative integer m, well, it also contains negative m, because negative 0 is 0. So when we take negative something in the ideal, we scale by negative 1. Negative m would be positive. So I cannot contain any negative integers either. So I is just 0, because it has to contain 0, but it contains no positive numbers, no negative numbers. And then I is 0z. Uniquely so, because for any over number n, we have that it contains n, which is not 0. Okay, so then we can suppose that otherwise I contains some positive integer. In that case, there's going to be a least positive integer it contains, because every subset of the positive integers contains the least element. It's called well-foundedness. So let's call it n. This is actually going to be n that is going to be generated by, we're going to see this in a moment. So now we want to show that I is generated by the least positive element it contains. Again, if it contains no, then it's 0, and it's generated by 0. So let's take some non-zero element. Now, if you have an element x is non-zero in I, then so is negative x an element of I, which is non-zero. It's an element of I because we scale by -1 is non-zero, because if x is non-zero, then negative x is not 0. Because otherwise, negative x equals 0, and then negative x is -0, so x is 0, which is not. So, okay, we've took some element x, which is non-zero in I, and then we have also the element negative x, which is non-zero in I. And then, because of how integers work, either x is positive or negative x is positive. Because if we take some non-zero element, either it is negative or positive. If it's negative, then negative, it is positive. If it's positive, then it's positive. So okay, we have either x is positive or negative x is positive. So consequently, because n is the least positive element of I, and x and negative x are elements of I, we have that n is less than equal to x and less than equal to, or less than equal to negative x. One of these. If x is positive, n is less than equal to x. If x is negative, then n is less than equal to negative x. Okay, so then we can write x as qn plus r by Euclidean division. I might have forgotten to mention that, but when we do Euclidean division, we want that what we divide by is less than the number we start with, at least for it to work out very nicely. Well, whatever. We can certainly do it if it is less than equal to what we start with, and we can do it here. So we can write either x or negative x as qn plus r for some natural number r less than n and some integer q. But now, r is qn plus r minus qn. That's just how adding and subtracting integers works, also how adding and subtracting things in the ring works, but here we are just looking at the ring of the integers. But qn plus r minus qn is x minus qn. And x minus qn is an element of I. Why is that? Oh, because n is an element of I. Right, so n is an element of I, which means any multiple of n is an element of I. So negative qn is an element of I, and then a sum of two elements of I is an element of I. So x minus qn is an element of I. So we have that r is an element of I. This is if x is qn plus r. If negative x is qn plus r, we get that negative x minus qn is r, and then again it's an element of I because negative x is an element of I, negative qn is an element of I. So either way, r is a natural element of I and is less than n, because that's how Euclidean division works. We picked r as the remainder. But there's only one natural number in I which is less than n, because n is the least positive one, so 0. R is 0. But then we have that either x is qn or negative x is qn, because it's qn plus r, and r is 0. So either x is qn or x is negative qn. So either way is in the ideal generated by n, it's a multiple of n. So we have shown that every non-zero element of I is in the ideal generated by n. Now also, the 0 element of I is in the ideal generated by n, because every ideal contains 0. Okay, so we have that I is a subset of nz. And conversely, if we have some element of nz is a multiple of n, but n is an element of I, and so a multiple of an element of I is an I. So nz is contained in I, and so I equals nz. So we have shown that every ideal in the integers principle is generated by a unique element, by a singleton, by one element. Not necessarily unique. In the integers unique if restricted to be natural. So now we kind of understand the whole ideal structure of the integers. Actually, a fact that's very important in ring theory, how the ideals in the integers look like. Not only ring theory, but also algebraic geometry. So the general definition that one makes is that a ring with this property is called a principal ring. So a ring where all the ideals are principal. So let me recall, an ideal is principal if it's generated by a singleton, so it's a multiple of all of the elements, multiple of some element. Sorry, an ideal in a ring is principal if it is the set of all of the multiples of an element of the ring. And if we have, so we've shown that in the integers all ideals are principal, and generally rings in which all the ideals are principal are called principal rings. And if they're domains, they're called principal ideal domains, or PIDs for short. So it's a big important family of rings. Actually, it's not that big, but it's an important family of rings. And the integers are a PID, principal ideal domain. We've shown that just now. Okay, now we can move on to what I was talking about. Actually, not quite yet, sorry. First, also to remark that Q, R, and C are also principal, but kind of for a boring reason, because all fields are principal. Why? Because the only ideals in a field are the 0 ideal, generated by 0, and the 1 ideal, generated by 1. So the singleton 0 and all of the field K. Why is that? Well, if you have a non-zero ideal, then it contains a non-zero element. Otherwise, all of the elements would be 0, and also it necessarily contains 0, so it equals 0. So let's say it has a non-zero element x. Well, now if you have any element y of k, if it's 0, it's in the ideal, and if it's non-zero, then y is y inverse times yx. We can divide because we're in the field. But y inverse times yx is a multiple of an element of I, of x. So, I don't think it's quite right. It should be, oh, sorry, this is not quite right. It's x, y is not y inverse times yx. I'm sorry again for the typo. This is x inverse times yx. But yeah, y inverse times yx is x. This should be x inverse times yx. Sorry for the typo. So fields are commutative, doesn't matter where we put it. But yes, we have that y is x inverse times yx. So it is a multiple of the element x in I. So it's an element of I because it's a multiple of an element of I by scaling. Because ideals are close to scaling. So any element of k is an element of I. And so we've shown that every element of k is in I. So k is contained in I, but also I is contained in k because it's an ideal of k. So I equals k. So every non-zero ideal is the ideal generated by 1. So we've shown that the only two ideals are these two. Note also they are distinct ideals because 0 is not equal to 1. Or if they were equal, then we would have that the ideal generated by 1 only contains 0. So 1 equals 0. But 0 is not equal to 1 because we're in the field. So they're two distinct ideals. And so in fact, they can actually characterize fields by the fact that the commutative rings, which have exactly two ideals. So we need that they're distinct because otherwise we have only the 0 ring. So we can prove this as well. If we have a ring, a commutative ring, which has only the ideals 0 and 1, so 0 and the whole ring R, then it's a field because if you have a non-zero element lambda, then lambda is contained in the ideal generated by lambda, but not in the ideal generated by 0 because it's non-zero. And because our ring contains only one moment. Yes, sorry. So because there's an element of the ideal generated by lambda, which is not in the ideal generated by 0, the ideal generated by lambda is the ideal generated by 1 because there's only two ideals. So the ideal generated by lambda is necessarily the ideal generated by 1. So lambda R is 1. The ideal generated by 1. Sorry, again, a typo. And so for some eta in R, we have that lambda eta equals 1 because 1 is contained in the ideal generated by lambda. So there's a multiplicative inverse. Also, 0 is not equal to 1 because these two ideals are distinct for the same reason as said above. Okay, so it's a little bit messy, but it's just an important observation we'll make of use later that a commutative ring is a field precisely when it contains two ideals. And these two ideals, two distinct ideals, precisely two distinct ideals. And these two ideals are necessarily diluted by 0 and by 1. And so we cannot drop the commutativity because we've required that fields are commutative. So for example, in the quaternions, we also have only two ideals, but they are not a field because they're not commutative. So we can do the same thing. We just need to drop the addition that R is commutative, and we get kind of so-called division algebras. And then the same characterization works there. But let's take the commutative rings, and then we know that the commutative ring is a field if and only it has exactly two ideals. Right. So next thing to consider is perhaps somewhat unmotivated at first, but we'll see it turns out to be a very important definition. And it's not the definition, yes, I've just put out on the screen, but it's the definition of a homomorphism. And one way of motivating it is by considering these two functions. The inclusion function of a subset into a set and the projection function of a set and the quotient set of the set by Congruences relation. So if you have some set x and a subset a and Congruences relation tilde on x, we have a function from a to x, like called I here, which sends every element of a to itself. And we have a function from x to the quotient set, which sends every element to its equivalence class. And these functions are called the inclusion and the projection. Inclusion of a into x and projection of x into the quotient set. In the context of rings, if we instead have a ring, an ideal, and a subring, we also have an inclusion of the subring into the ring, and we have a projection of the ring to the quotient ring. And these two functions satisfy these properties. And okay, this seems like a mess of properties, but really all these properties are saying is that these functions behave well with the ring structure, that we can first apply the thing in the ring structure, for example, the addition, and then the function, or first apply the function, and then to think the ring structure, the addition. So for example, these functions map sums to sums, or they map additive integers to additive integers, 0 to 0, products to products, and 1 to 1. And functions of this kind are what are called homomorphisms. So if you have two rings, A and B, a homomorphism from A to B is a function from A to B, which has these properties. But actually, it suffices to require these properties, that sums at inverse, actually, yeah, they have properties from earlier, but actually, it suffices to require only that sums, products, and 1 are preserved. The fact that additive inverses are preserved follows from these, because first of all, we have that 0 is also preserved if these things are preserved, because f of 0 is f of 0 plus f of 0 minus f of 0. We just added 0 as f of 0 minus f of 0. But f of 0 plus f of 0, because f preserves sums, is f of 0 plus 0, so f of 0. So this is the same thing as 0. And also we have now that f of x plus f of minus x is f of x minus x, because f preserves sums, so f of 0 is 0, what we've just seen. So subtracting f of x, we get that f of minus x is negative f of x. So again, what we're doing, we've seen that for inclusions and projections of subrings into rings and rings onto quotient rings, we have these properties, that these functions preserve sums, additive inverses, 0, products, and 1. And just abstracting away, we notice that it suffices to only require that functions preserve sums, products, and 1, and then the other properties follow. It's kind of similar to how, when defining a ring, it suffices to exhibit the addition multiplication. Okay, so an example you might have seen is complex conjugation, and this function from the complex numbers themselves, which maps a plus bi to a minus bi. And you can check that sums, 0, 1, products, and additive inverses are preserved. Actually, in a sense, this is the only good homomorphism from C to C. It's the only continuous automorphism, whatever that means. Okay, so this notion of homomorphism, and again, it might seem a little bit unmotivated, like why are we considering these abstract properties of functions? But there's kind of a good way of characterizing them we'll get to in a moment. But first, let's consider a very important family of homomorphisms. Namely, there's this fact that if you have any ring R, there's a unique homomorphism from the integers to R. Now we know that any homomorphism has to map 0 to 0 and 1 to 1. So we know where 0 and 1 map to. But also we know that the integer 2 is 1 plus 1. So because homomorphisms presume sums, we know that 2 has to map to 1 plus 1 in the ring R, and 3 to 1 plus 1 plus 1, etc. Essentially, we're saying that there's a unique way of interpreting the integers in any ring, so in a way that the interpretation works as one would expect, that 3 is 1 plus 1 plus 1, etc. So perhaps in the example with multiplying matrices, we had that 2 is 1 plus 1. We can actually do this with any integer. There's a unique way of doing that. And so we kind of can interpret the integers internal to any ring. So yes, we can prove that there's a unique homomorphism. So for example, in z modulo 4z, we had this 4z plus 2, which squares to 0. It's actually just 2. And interesting enough, now in this ring, you have the 2 times 2 equals 0. Again, this seems somewhat absurd, same way we're talking about 0 equating to 1, but it's just kind of the abstractness we went to. And one should remind oneself that the 2 written here is not literally the integer 2, it's the integer 2 interpreted in this new ring, z modulo 4z. So what happens here is this homomorphism from the integers to z modulo z is not injective. The integers interpret in a way that gives us these weird properties like that 2 squares to 0, or that like 3 times 3 equals 1. So one way of measuring non-injectivity of homomorphisms is called kernel construction. When you have a homomorphism of rings, its kernel is the preimage of 0, so everything maps to 0. And well, clearly, first let's note above the kernel of the map from z to 4z, z modulo 4z, the unique one, is just 4z, because the kernel of a projection is just the ideal that one quotienting by, because that's by definition what the ideal does on the quotients. It's the set of everything that becomes 0. But more importantly, the kernel of any injective map is 0, because the only thing that maps to 0, well, first of all, we know that 0 has to map to 0, but if f is injective, nothing else can map to 0, because 0 already maps to 0. But the converse is also true. So actually computing the kernel of a map is a very useful way of checking if it's injective or not, as long as it's a homomorphism of rings. So the dilemma is, if you have some, actually, that's not quite dilemma yet. First, we can notice that this quotienting generalizes to the fact that the kernel of a homomorphism is always an ideal. It's kind of always a matter of being in a way a quotient. So the fact is that if you have a homomorphism, the kernel is an ideal, and we have that the equivalence relation associated to this ideal, that A is similar to A prime whenever A minus A prime is in the kernel, is the same one that we get associated to F, that A is similar to A prime whenever F of A equals F of A prime. So F of A is equals to F of A prime whenever F of A minus A prime is 0, because that's how homomorphisms work. We have that F of A minus A prime is F of A minus F of A prime, because homomorphisms preserve additive inverses and sums, and F of A minus F of A prime is 0 precisely when F of A equals F of A prime. And well, F of A minus A prime gets mapped to 0 precisely when A minus A prime is in the kernel, because that's the definition of the kernel. So for our lemma, we just have to check that the kernel is an ideal, then we get this equivalence relation to congruence. Now, why is the kernel an ideal? Well, it's a computation. We check that all of the properties of our characterization of ideals are satisfied. First of all, 0 is in the kernel, because 0 maps to 0. And if you have A and B in the kernel, their sum is also in the kernel, because their sum gets mapped to the sum of the values, but the values are 0 because they're in the kernel. So they get mapped to 0. And the same thing with scaling. You can kind of take out scaling. If you have A in the kernel, and we have some element R of our ring, capital A, then f of R times A is f of R times f of A, because our function preserves products. So f of R times f of A is f of R times 0, because A is in the kernel and this is 0. The same thing on the other side. So we get the kernel satisfies this characterization of ideals we've proven before, so it's an ideal indeed. And thus we can associate an ideal on the domain ring of any homomorphism of rings. So in particular, we can look at kernels from these maps from the integers. If you have any ring R, as you've seen, there's a unique map from the integers to R, that's homomorphism. And the kernel of this map is going to be an ideal of the integers. And we've seen that all of the ideals of the integers look as principal ideals. They are nz for some unique natural number n. Then this unique natural number n is called the characteristic of R. So the way one gets the characteristic of a ring, one looks at the homomorphism from the integers to the ring, the unique one, and one asks oneself the question, what is the smallest non-zero natural number that gets mapped to 0, the generator of the kernel? If there's none such, then the generator of the kernel is 0, then the function is injective, the homomorphism, as we'll see in a moment. Otherwise, it's, yes, the smallest amount of ones one has to add to itself in the ring to get 0. So for example, in z modulo 4z, the characteristic is 4, because 1 plus 1 plus 1 plus 1 is 4, but 3 is not 0, sorry, 1 plus 1 plus 1 is 4, that's 0. But 3 is not 0, 2 is not 0, 1 is not 0. So the characteristic of a ring, if it's non-zero, is the smallest, so say, integer interpreted in the ring. It's positive and interprets to 0. And if it's 0, then the interpretation of integers is injective. So, okay, this is what I was talking about before. The converse of our before statement that kernels of injective maps are 0 has also the converse of it true. If the kernel of a ring homomorphism is 0, the ideal generator is 0, then the ring homomorphism is injective. And it's just a straightforward computation. So first of all, if so this is an if and only if the ring homomorphism is injective, then the kernel is 0. But conversely, if the kernel is 0, and we have that f of a equals f of b, then again, because f is a homomorphism, f of a minus b is 0, because it's f of a minus f of b. But then a minus b is in the kernel, so in the ideal generator is 0, so a minus b is 0, because it's the only element of the kernel, and so a equals b, so f is injective. So by this lemma, we know that a map from the integers to a ring R, the only homomorphism from the integers that exists to any ring R is injective whenever the kernel is 0. So whenever the ring has characteristic 0. Because the kernel being 0 means that the kernel is generated by 0, which was also definition, which was our definition of the characteristic, the natural number which generates the kernel from the map from the integers to our ring. So when this map is injective, it means that the integers in our ring behave like normal integers. There's no non-injective interpretation. You cannot have overlap. 1 plus 1 equals 4, and 5 equals 123. Of course, if an equation is true in the integers, it's going to be true in the integers interpreted in any ring, because our homomorphism brings over. So in any ring, 2 plus 7 equals 9. But what might happen is that we have non-injectivity, and for example, 1 plus 1 equals 4, or as we've seen before, 4 equals 0. And when this doesn't occur, that's exactly when the ring has characteristic 0. So, for example, the integers, the rationals, the reals, and the complex numbers have characteristic 0. But if you take z modulo nz, well, it's the quotient of z, the kernel from the map from z to this quotient is going to be nz, because there's only one map, the projection in this case. And so the characteristic is n. And so, for example, in z modulo 5z, we have that 5 equals 0. Or in z modulo 10z, we have that 10 equals 0. Right. So something to note is that if we do homomorphisms after each other, we get a homomorphism again. It's kind of a computation. We can check that first of all. Well, we've seen that it suffices to check that one is preserved and sums and products are preserved. So we can check that one is preserved because f of g of 1 is f of 1 is 1 because g preserves 1 and f preserves 1. And also for question marks, I like to use this notation question mark in plus times. What I mean is that whether one takes plus or times, this equation holds. If one first does operation on some elements x and y of A, then applies g and then applies f. Well, g is a homomorphism, so it's the same thing as doing it on g of x and g of y in B, and then applying f. F is homomorphism, so it's the same thing as doing it on f of g of x and f of g of y in C. So in particular, we've seen that the composition f composed with g preserves question mark. So either plus or times. So in particular, it's a homomorphism. And one thing one gets when one knows that compositions of things are again things like what one composes, kind of a category theoretic notion is the notion of an isomorphism. So a ring isomorphism, which is a bijective ring homomorphism, we can actually equivalently say that a ring homomorphism from A to B is an isomorphism if there's a ring homomorphism from B to A which kind of undoes it, so an inverse. So the inverse function is also it exists and it's a ring homomorphism. So one can check that the inverse of a ring isomorphism is again a ring isomorphism, and also the composition of ring isomorphism is a ring isomorphism. Okay, so an example of ring isomorphism is when we take some ring R and quotient by 0. The reason it's an isomorphism is because, well, we've seen it's a projection, so it's a homomorphism, and it's injective because the kernel is 0, because we're quotienting by 0, we quotient by some ideal. The kernel of the projection to the quotient by some ideal is the ideal. And it's surjective because any element of the quotient ring is by definition the equivalence class of some element in R, so the image under this projection. So another example to kind of illustrate the point of the notion of an isomorphism is that let's take these two rings, R1 and R2, who have the following multiplication tables. So R1 consists of lowercase a and lowercase b, and R2 of capital A and capital B. And we can simply map lowercase a to capital A and lowercase b to capital B, R1 to R2. And this is going to be an isomorphism rings. It's a bijective function, it's a homomorphism, it preserves all of the structure. Essentially, what it means for two rings to be an isomorphic, or for a map between rings to be an isomorphism, is that one can rename the elements of one ring to another, and all of the structure is preserved. So indeed, these two rings can also be seen to be Z modular to Z, isomorphic to Z modular to Z. Usually, one doesn't really differentiate between isomorphic things because they're the same thing up to renaming. So sometimes somebody will write that X equals Z modular to Z. What I mean is it's isomorphic to Z modular to Z as a ring, but it's kind of evident what one means because it's really being the same thing as Z modular to Z, except having perhaps different elements, different names to the elements. Okay, so another important thing that comes with isomorphism is the notion of an embedding, and that's just an isomorphism to a subring. So for example, I might have something which is isomorphic to the integers, and I can map it into the rationals, so a function from A to the rationals, a homomorphism, which is going to be an isomorphism to the subring of the rationals of the integers. So we can kind of view it inside. A embeds into B if A can be viewed inside of B. Okay, so one thing I can do, kind of dually to the kernel, is take images. And if you have a ring homomorphism from A to B, its image is the set of its values. So we can check that's a subring. It's kind of just a computation. And what one gets is it's called first isomorphism theorem for rings. This is a theorem or a family of theorems that holds in many contexts in any algebraic structure, something studied by universal algebra. But the statement is just the following. If you have any ring homomorphism from ring A to ring B, then the function from the quotient of A by the kernel of F, again, we've seen the kernel of F is an ideal of A, so we can quotient, to the image of this map F, given by the following expression, we map an equivalence class of X to X for X and A. First of all, it's well defined. It makes sense to define this map like this. So regardless of which representative we pick, F maps in the same element, and it's also a ring isomorphism. So essentially, when we quotient by the kernel of a map, we just get its image, which makes sense because quotient here by the kernel, we've seen is the same thing as identifying two elements of our ring A whenever they have the same image. So we're essentially just thinking of them as their image. So we get their image as after isomorphism, by this isomorphism. So let's check. Kind of again a computation of sorts, but it's good to familiarize yourself with the notions. So first, let's check that it's well defined. If you have two representatives x and y for the same equivalence class in A modulo the kernel, well then the difference is in the kernel because they are the same. They are representatives of the same equivalence class. So they're equivalent under the congruence corresponding to the kernel, which means that the difference is in the kernel. Well, that means that f maps the difference to 0, and because f is a homomorphism, it means that fx equals f of y. Because if fx minus y is 0, then f of x minus f of y is 0, so fx equals f of y. So this shows that this f tilde is well defined because the value of f tilde on the equivalence class doesn't depend on the representative we use for the equivalence class. It makes sense to consider this function. It is a function. Now, let's check injectivity. If we have that f tilde maps two equivalence classes to the same value, well, then by definition, we know that fx equals f of y if x and y are representatives of these equivalent classes. Well, but then f of x minus y is 0. Again, we just subtract f of y on both sides, and it's a homomorphism. So then x minus y is the kernel, but then by definition, the equivalence class of x is the same as the equivalence class of y. So we've checked that f is injective, f tilde is injective. F, of course, is just an arbitrary homomorphism, but f tilde is injective once we quotient the kernel. It kind of makes sense. We've made the kernel 0 by quotienting it, so now it's injective. And we've made the image of the codomain of the map the image, so we made it surjective. We're kind of forcing f to be an isomorphism. We've made the kernel 0, and we've made the image the whole codomain. And how one verifies this formally, if we have something in the image of f, in the codomain of f tilde, well, then there's some x and a with fx equals y, if y is the thing in the image, just by definition of image. And then f tilde applied to the equivalence class of x, y, by definition of f tilde. So y is an image of f tilde. So f tilde is surjective. Again, we've just kind of forced the surjectivity onto this map. Now, lastly, we have to check this homomorphism. So this would be a ring isomorphism. And, well, we just check. F tilde of 1 is the f tilde of the equivalent class of 1, because, well, when I write 1 here, I mean the 1 in A modulo cure f. But in this quotient ring, as we've seen, 1 is the equivalent class of 1 up above in A. So when we apply f tilde to equivalence class of 1, we get f of 1 by definition of f tilde. But f is a homomorphism, so it's just 1. So f tilde of 1 is 1. And again, if we take some operation, we do f tilde of the equivalence class of x operation of the equivalence class of y. Well, by definition of the quotient ring, f tilde, the equivalence class of x used some operation in equivalence class of y is the same thing as the equivalence class of x uses operation in a y. When we apply f tilde, it's the same thing as fx question mark y, which is because f is homomorphism, fx question mark fy. And so by definition of f tilde, the same thing as f tilde applied to equivalence class of x question mark f tilde applied to equivalence class of y. So by the characterization of homomorphisms, we've proven, maybe I didn't prove it, but we've seen f tilde is a homomorphism, and we've checked it's injective and surjective because we've kind of made it to be, and so it's an isomorphism. And it's kind of a technical result to some extent, but it's very useful in proving that things are isomorphisms sometimes. Okay, now we can come to motivation for why one can consider homomorphisms. Really, we've seen these natural functions that appear when we consider rings. We have inclusions of rings and we have quotients of rings. So, sorry, projections of rings onto quotients. These really very natural functions because we do want to look at subrings of rings. It's a useful way of, say, constructing new rings. And we want quotient rings. It's also a useful way of constructing new rings. And often we want to identify things in the ring. Also, another thing that's pretty intuitive is the notion of an isomorphism of rings. If two rings have the same structure, except they have different names of the elements, we want to consider the map with renamed elements, an isomorphism. So we have these three kinds of functions between rings, inclusions, projections, and isomorphisms. And a homomorphism can be understood as an arbitrary composition of these. So the lemma is the following, or the theorem. If we take the class of all homomorphisms, so by class I just mean something like a set, except it's kind of bigger, this technical difference. A class is an arbitrary collection of sets, and a class might not be a set to avoid contradictions like Russell's antinomy. So take the collection of all the homomorphisms between rings and compare it with the collection of all the smallest class of functions between rings that contains projections, isomorphisms, and inclusions, so all kind of natural examples of functions between rings, and contains the compositions. So essentially, this class consists of precisely the set of all the class of all the compositions of projections, isomorphisms, and inclusions. It contains any projection, any isomorphism composed with a projection, any inclusion composed with an isomorphism composed with a projection, etc. this is going to be the same thing as the classical homomorphisms. So we can understand homomorphisms precisely as compositions of projections, isomorphisms, and inclusions. And the way to see that is, well, first of all, any projection, inclusion, and isomorphism is a ring homomorphism. So and any composition of ring homomorphism is a ring homomorphism. So the classical ring homomorphisms contains this smallest class of all functions obtained as compositions of projections, isomorphisms, and inclusions. Because any composition of projections, isomorphisms, and inclusions is going to be a composition of homomorphisms, so it's going to be a homomorphism. So we know that the smallest class of functions containing projections, isomorphisms, and inclusions is contained in the classical ring homomorphisms. Now we only need to see the reverse inclusion, that every ring homomorphism can be decomposed into a composition of projections, isomorphisms, and inclusions, and that's what the first isomorphism theorem comes in. We can look at this diagram. So say we have some ring homomorphism from a ring A to ring B, and then what we can do, we can first project A down to the kernel, the quotient by the kernel of F. Then we can apply an isomorphism to the image, this F tilde we constructed above, and then we can include the image in B. And this composition is going to be exactly F. So in other words, we can think of ring homomorphisms as inclusions of quotients. If you have a ring homomorphism between rings, it's the same thing as including a quotient. It's kind of a very more visual way of thinking about ring homomorphisms. And perhaps it's a more motivated way of thinking about them than just writing down the formal definition that we require these properties. Yes, it's perhaps somewhat unintuitive notion, but we can think of them as just compositions of projections, isomorphisms, and inclusions. So kind of a homomorphism is an embedding of quotient. Just a way of thinking of it. Okay, now we come to something I've mentioned way too earlier, namely asking when quotients of rings have certain properties. For example, for which ideals of a ring the quotient is a field. And this is where our characterization of fields stands as rings with precisely two elements, precisely two ideals, which are commutative, comes in. Because we can answer this question by looking when the quotient by I contains precisely two ideals. And for that, we first want to look at what the ideal structure in the quotient looks like. And for that, we have a few kind of technical results that are quite useful and in fact very important for algebraic geometry. And in fact, this might seem like a kind of silly question, or not necessarily silly, but kind of a curiosity, but actually it turns out to be very important what concerns, say, algebraic geometry. Because studying quotients and their properties actually turns out to have very geometric ramifications. So first, let's look at this lemma, which is kind of a generalization of the fact that the kernel of homomorphism is an ideal. If you have some ring homomorphism between rings from ring A to ring B and some ideal J of B, we can take the pre-image of J in A, set of all elements of A which map into J. So if J is the zero ideal of B, this is just the kernel of F. And then we know it's an ideal of A. But actually, by this lemma, it's always an ideal of A, no matter what J is, as long as it's an ideal of B. So pre-images of ideals are ideals. And actually, it's also kind of a nice exercise in practicing your ring theoretic notions, like what an ideal is, what ring homomorphism is, etc. So it's left as an exercise. Now, dually, it's not true that the image of a homomorphism and the image of a ideal on the homomorphism is an ideal. It is true, however, if we say that the homomorphism is surjective, so if we view it as an ideal instead of the image. So if you have a surjective ring homomorphism between rings, an ideal of the domain, then the image of the ideal is an ideal of the codomain. Again, I'll leave it as an exercise. It's good to practice your ideal notions and ring homomorphism notions, etc. And this is a pretty long talk, so if I give the proof of everything, it would take double as long. So let's leave it at that. But now that we know these two things, we can understand the structure of the ideals and the quotient of a ring by an ideal, and consequently understand when it's a field by asking that they're exactly two. So how do we do this? Let's say we have some ring R and some ideal I of R. And then we can consider the projection from R to R mod I, it's called P. Then ideals of the quotient ring, modulo I, correspond precisely bijectively with ideals of R which contain I. So again, an ideal of the quotient is the same thing as an ideal of what we were quotient that contains the ideal of the quotient by. So how do we make this correspondence? If we have an ideal J of the quotient, we can simply take its pre-image under P, we see it's an ideal, and get an ideal of R which contains I. It's going to contain I because the pre-image of an ideal of R modulo I is going to contain the pre-image of 0, because 0 isn't any ideal in R modulo I, and taking pre-images is monotone. And so we will have that any pre-image of an ideal of R modulo I contains I in R. And so we have this function which takes an ideal in the quotient and gives us an ideal of the ring we quotiented that contains I. Now let's check its bijective, and then we'll have this insight into how to think about ideals of the quotient. So to see surjectivity, let's take some ideal J of the ring R, which contains I, and we want to write it as a pre-image of an ideal of the quotient. Now, by the lemma on top of this page, P is surjective, so the image of J is an ideal of the quotient. And then we can take the pre-image of the image, and we're going to get J. And this shows P is surjective. Now, to see that P is injective, note that if the pre-images of two ideals of the quotient are the same, well, then the ideals, just the images of the pre-images, then they're also the same, because the pre-image is the same, so the images are the same, so the ideals are the same. So we get this bijective correspondence between ideals of the quotient and ideals of the ring we started with that contain the ideal we quotiented by. And this can help us answer our question of when a quotient is a field, because a quotient is a field precisely when it has exactly two ideals. We've seen that before. So what we know now is that a quotient of a commutative ring by an ideal I is a field whenever there are exactly two ideals of our ring that contain I as a subset. And they're going to be I itself and the whole ring, necessarily, because these are examples of such ideals. So these ideals are called maximal ideals, and we have proven that an ideal of a commutative ring is maximal whenever the quotient is a field. And it's a very kind of important characterization of when the quotient is a field, and a very important notion of maximal ideal. In a sense, maximal ideals of rings are the points geometrically of the rings, the closed points. Again, this is algebraic geometry, and I'm not going to elaborate on that too much, but we'll see that in the algebraic geometry lectures. Okay, so maybe an example in the integers, the ideal generated by 2 z is maximal, because the quotient is a field. We've seen that, I've mentioned that. Also, alternatively, you can just directly check. If you have an ideal of the integers, which contains 2, so it contains the ideal generated by 2, it's the same thing as containing 2. Then let's write this ideal as nz. We've seen you can do that, so natural number n. Well, then we know that 2 is contained in nz, so 2 is a multiple of n. Well, if 2 is a multiple of a natural number n, then n is 1 or 2. There are only two ideals then. So 2z is maximal. On the other hand, 4z is not maximal, because, well, we've seen the quotient is not a field. It's not even a domain. But also we can just directly check 2z contains 4z. But 2z is neither 4z nor z. So there are three ideals of z modulo 4z, not 2. There's z modulo 4z, 2z modulo 4z, and kind of 0z modulo 4z. These are all three ideals of z modulo 4z, and they're not 2, so it's not a field. And so 4z is not maximal. Okay, we can now do the same spiel, but just take instead of fields, domains. And actually, it turns out kind of simpler. Oh, well, in a sense, it doesn't. We just get a more complicated notion of ideals that correspond, namely prime ideals. So we can ask the same question: when is the quotient of commutative ring in domain? And well, by definition, a domain is a commutative ring such that 0 and 1 are distinct, and whenever a product is 0, one of the factors is 0. So we can just read this kind of out in the quotient ring and read out the condition on the ideal. So if we have an ideal I of a commutative ring R, the quotient R modulo I is a domain if and only if I is not the whole of R, and if and only if also if the product of A and B is an I for some elements A and B and R, then either A is an I or B is an I or both are an I. So why is this true? Well, I is equal to R exactly when in the quotient R modulo I is I modulo I, so just 0, because we've identified I with 0. So when the quotient is a 0 ring, and whenever 0 equals 1 in the quotient. So because a domain needs to satisfy precisely 0 not equals to 1, this is the same thing as asking that the quotient satisfy that the ideal we quotienting by is not the whole ring. Because always, well, the quotient by ideal is the 0 ring, whenever the ideal is the whole ring. And because we explicitly want the domain not to be a 0 ring, we explicitly need to require that the ideal we quotienting by is not the whole ring. And now the condition on products, well, in the ideal, the fact that AB is an I, implying that A is an I or B is an I, when we read it out in the quotient modulo I, same thing as saying that if AB is 0, then A is 0, B is 0. Because we will just apply the projection, and I maps to 0. And the projection of homomorphisms, so we're saying that the projection of A times the projection of B is 0, implies that the projection of A is 0, or the projection of B is 0. And this is the same thing, because we can write every element of the quotient as a projection. So we can just we identifying I with 0, saying that AB is an I is the same thing as saying that AB is 0 in the quotient. AB plus I, the quotient is 0. 0 plus I. Okay, so this is the definition we get for ideals, or the property of ideals. Such ideals are called prime. So an ideal is prime if it's a proper ideal, meaning it's not the whole ring, and whenever a product is within it, one of the factors is within it. And we've seen just kind of with definition of primality that ideal of a ring is prime whenever the quotient is a domain, precisely when. Okay, so let's look at some examples. And why it's called a prime ideal? If we take some positive integer n, then the ideal generated by n within the integers is prime precisely when n is a prime number itself. And if it is a prime number, then it's also maximal nz. So let's prove this. If n is prime, then nz, if it is contained in some ideal I, writing I as mz, because all ideals are principal in the integers, it's in a principal ideal domain, we get that m is an element of nz, and thus an I. No, sorry, n is an element of nz, and thus an I. So n is an mz, so m is divisible by n. No, sorry, n is divisible by m. And so m is either 1 or n, because n is prime, so it has only two positive divisors. So there are only two possibilities. There are only two ideals above nz, so nz is maximal and also prime, because fields are domains. So if the quotient is a field, it's a domain, so all maximal ideals are prime. So we've seen that, we've shown that if we generate the ideal by a prime number in the integers, we get a maximal ideal, in particular also a prime ideal. Now, if we have a prime ideal in the integers nz, or actually, if we have an ideal nz in the integers and n is not prime, well, we can write n as a times b with some integers a and b which are positive, greater than 1, and less than n. That's what it means to be prime in the classical sense, in positive integers. Well, if this is the case, well, then we have that a is not 0 modulo n, and b is not 0 modulo n, so in the quotient ring, because, well, for a to be 0 modulo n would mean that a minus 0 is an nz. So a is a multiple of n, but a is less than n, and greater than 1. Same thing for b. So a is not 0 and b is not 0. But a times b, it is an nz, so it's equal to 0 modulo n. So we have that z modulo nz is not a domain. In other words, we have simply that a is not an nz, b is not an nz, but ab is an nz, violating that nz is a prime ideal. So it follows that if nz is a prime ideal, n has to be prime, because otherwise we don't get the prime ideal. At least when n is a positive integer. That's not true for 0, at least with this classical notion of primality. So yes, this is kind of a characterization of prime and maximal ideals in the integers. An ideal is prime if and only if it is either the 0 ideal, because the 0 ideal in a domain is always prime, because we quotient by 0, we get the domain back. Or it's of the form nz when n is a positive integer and it's prime. And no other ideal is prime. So this is why it's called prime ideals. It's also kind of the property we require is kind of primality, that if p divides ab, p divides a, or p divides b. It's kind of a characterization of being prime in the integers as well, somewhat. So yes, in general, in most rings, maximal ideals are not prime. It's just a coincidence in the integers. And also in the integers, not all not all prime ideals. Sorry, I said something wrong. I meant, yeah, maximal ideals are of course always prime because fields are domains, but not all prime ideals are maximal. That's what I meant. In the integers, it's true that all prime ideals are maximal except for the ideal generated by 0, but in most rings there are many prime ideals which are not maximal, even non-zero ones. Okay. So one thing we also get about domains is that we can consider their characteristic. And the characteristic of a domain is, again, the natural generator of the kernel of the map from the integers. Well, by the first isomorphism theorem, the quotient of the integers by the kernel of this map is a subring. It's isomorphic to the image of this map. So it's isomorphic to a subring of the domain D. But these domains, so every subring is a domain. So this means the quotient, z modulo kernel, is a domain. Well, we've seen then that the kernel is either generated by 0 or generated by a prime number. So this shows that a domain necessarily has either characteristic 0 or a prime characteristic. It's kind of a property of domains. It's sort of a reducibility of sorts. We'll talk about reducibility a bit later. It's a different related notion. Okay. So one thing we can say here is that because subrings of domains are domains, we get the pre-images of prime ideals are prime. And it's kind of a useful, it's a very useful lemma in algebraic geometry as well. It's very good to know. It has geometric ramifications. So why is that? Well, let's take some homomorphism of commutative rings F from A to B and take some prime ideal P of B. We want to show that the preimage of P under F is a prime ideal of A. Well, we have the projection, which is a homomorphism from B onto the quotient, P modulo the prime ideal P. And we can consider this map. We first apply F and then we apply the projection. So P composed with F. And now we can apply the first isomorphism theorem to this map. The kernel of this map is everything which maps to 0. So everything such that P applied to F applied to this thing is 0 in B modulo the prime ideal. So it's everything. So the projection of something is 0 in the quotient whenever that something is inter-ideally quotienting by. So it's essentially just the preimage of the prime ideal P under F, this kernel of G. So applying the first isomorphism theorem, we get that A modulo the kernel of G, so A modulo the preimage of the prime ideal P, it's isomorphic by the first isomorphism theorem to the image of G, which is a sub ring of B. Wait, this should be a subring of B modulo the prime ideal, I'm sorry. No, a typo. So we have that G goes from, so we first go A to B, and then B to B modulo the prime ideal P. So here it should say G of A contained in B modulo the prime ideal P, because that's where G goes to. And then that's a domain. B is not a domain. Yeah, that's a typo. This should be A. B is not a domain, but B modulo the prime ideal P is a domain. So G of A is contained in B modulo the prime ideal. So G of A is a domain itself, because it's a subring of a domain. But then we've seen that A modulo the preimage of P is a domain. So the preimage of P is a prime ideal because the quotient by it is a domain. Yeah, sorry for the typo. It should be B modulo prime ideal. Yeah. Okay. So subrings of fields are not fields. So it's not true that the preimage of maximal ideal is maximal. However, we can fix that if we take if we take surjective homomorphisms. Another thing we can do. So that's a remark. So we can see this, by, for example, if you take the inclusion of the integers into the rationals, the prime ideal 0 into rationals is maximal because the rationals are a field, only two prime ideals, so 0 is a maximal ideal. The quotient by it is the rationals. But if you take its preimage into the inclusion, we just get 0 into integers, which is not maximal because say it's contained in 2z, but 2z is not the whole set. Okay, that'll be all for the second part of the talk. Let's again ask if there's any questions, anything unclear. I mean, okay, and there's a lot of material I'm kind of rushing through somewhat, but it's all kind of very relevant things to algebraic geometry, and I hope that even if maybe now I'm going a little bit fast-paced, these things can be referenced back to the recording, and they're still useful. So, okay, any questions? Again, it's fine if it's a stupid question, so to say, but it's useful to kind of just, yeah, think about questions, ask questions. Also, it's good for me to take a little break of talking. Yeah. Okay, so somebody's asking about the importance of the characteristic of a ring. So the theory, say algebraic geometry over commutative algebra over a field of or ring of positive characteristics, so a ring. So again, let me remind first the definition of characteristic. The characteristic of a ring is the unique natural number which generates the kernel of the unique homomorphism from the integers to this ring. For example, if you take the ring z modulo 2z, there's a unique homomorphism from the integers 2z modulo 2z, and it's the quotient, the projection. And as a projection, its kernel is 2z, and so it's generated by 2. So the characteristic is 2. Now, why we care is because the characteristic in PE2 tells us that 1 plus 1 equals 0. It's a pretty kind of strong statement that 1 plus 1 equals 0. We can prove a lot of stuff using that. And the theory actually starts to quite differ. So something you'll get sometimes, first you'll get yeah, so actually there's a very interesting thing I can mention, but first let me mention that often in many theorems, say also in linear algebra, you'll want to require that the field or ring you work with has not characteristic 2. Because if you have a characteristic 2, 2 equals 0, and you cannot divide by 2, for example, in the field. And that might affect things. So there are some various funny theorems where it's you assume that the characteristic is not one of the first 53 prime numbers or something like that. Because if it's one of the first 53 prime numbers, a bunch of stuff goes wrong because small numbers have various kind of relations between them, and you just get things that are zero and you cannot divide by them. So one reason we care about the characteristic of a ring is that we, especially in the case of fields, the characteristic of a field is important, so we know that you can say divide by 2 or divide by 3. Even though in a field, we might not be able to divide by 2 because 2 equals 0. So that's one reason we might care about the characteristic. I mean, it's kind of a very silly reason. It's not really saying much. But there's a much more interesting reason why characteristics are important. This has to do with so-called analytic geometry. And it's a very advanced topic in a sense, and I won't be able to say anything too specific about it, both for not having enough background developed here, and both for myself not being too familiar with it. But what one can do when one's studying algebraic geometry in characteristic zero. So characteristic zero is when we interpret the integers injectively in the usual way. So for example, the field of the rationals, the field of real numbers. So usually algebraic geometry is done over a field. So if we have a field of characteristic zero, something that turns out for many fields of characteristic zero, and it says almost, well, actually all fields of characteristic zero, we can think about the purely algebraic notions in terms of notions of, say, complex analysis. We can make a relation, like there's a relationship, it's called Gaga, it's a little name, but it comes from a name of a paper of Sir, Geometrie Algebraique, Geometrie Analytique. And there he makes a kind of correspondence between an algebraic geometric way of viewing things, algebraic objects in characteristic zero, and viewing analytic objects in characteristic zero, like complex manifolds. So, for example, if you can prove a purely algebraic theorem about ideals in a ring by looking at complex manifolds. But you can only do this if you you want a field, and then you walk in a polynomial ring, we'll get to that, but you can only do this in characteristic zero. You cannot use analysis in characteristic 2 quite the same way. It's more difficult to, you can still do a kind of manifolds over a ring of characteristic 2, but it's no longer the usual analysis is algebraic geometry. So in order to use the usual tools, and actually also the other way around, there are many theorems of differential geometry you can prove, especially complex geometry, you can prove with algebraic geometric means by interpreting them algebraic geometrically. For example, there's a theorem that you can think of any appropriate complex manifold as a algebraic variety over the complex numbers. Whatever that means, we'll get to that in lectures. Then you can prove theorems about these manifolds using algebraic geometric means. And for that, we really need characteristic zero. We get characteristic zero because we started with characteristic zero in a sense, but characteristic zero matters because characteristic zero is what you have in fields that you usually work with in analysis, for example. So that's kind of one reason why you want to care about characteristic. You want to say exclude positive characteristic. Often people will work either in positive characteristic or in characteristic zeros. For example, I also research algebraic geometry. I work in positive characteristic mostly. And the theory looks kind of different. You get different cases depending on characteristic for your statements, etc. So there's just the differences in theory that you get when studying rings different characteristic. It's just a property of ring having a certain characteristic, and it's just the amount of times you need to add 1 to itself to get 0, the least amount of times. And if it's impossible to add 1 to itself some amount of time to get 0, the characteristic is 0. That's what the thing about the characteristic. And again, it's important to know when 1 plus 1 equals 0. And so for example, so you can divide by 2. And so that's why we care about the characteristic. I know it's a very general answer. Why do we care about anything at all? It's a somewhat subjective question, so I'm not sure if I can say much more about that. I hope that somewhat illuminates the notion of characteristic and why we care about it. Does that help somewhat? Okay, good. Nice. Any other questions? Mm-hmm. Okay, doesn't seem like there are any other questions. I guess we can move on. And so now we'll get to part of the talk where I'll introduce some more algebraic geometric way of viewing things somewhat. I'm not going to get into too many technical details. And first I'll talk about just purely algebraic notion to kind of put it into context. And also this notion of modules and algebras. It's a very important notion, and I have to bring it up somewhere because we are going to mention it at least in the lectures. It's actually a very intuitive notion. I'll get to it in a second. But then after this, I'll move on to talk about the sort of algebraic geometric way of viewing things. but in a classical situation, so it's more intuitive. And then maybe this will be somewhat helpful once we do these things in an abstract purely algebraic situation to think back to have an intuition. But first, yes, let's continue with the pure algebra. And for that, here's this notion of modules over a ring. And you can do modules over any ring. It doesn't need to be commutative. But if you have non-commutative rings, it's kind of more messy. So let's just stick to commutative rings. Instead, in algebraic geometry, we mostly care about commutative rings. So let's pick some commutative ring R. A module over R, or R module, is specified by specifying a set M. And then we want, again, some stuff on M. We want a binary operation of addition and a unary operation of subtraction, as well as an element 0 of M. We have these three things. And then we also have, additionally, something we didn't have before with rings. It's a scaling operation. I mean, we had multiplication in rings. It's kind of similar. And that's kind of what algebras are about later. But here, all we want is we want a function which is no longer an operation, but it takes an element of our ring R we started with, and it takes an element of our module M, and it gives you an element of the module M. It's kind of scaling. So you usually note that like multiplication, lambda v, where lambda is in your ring and v is in your module. So you call elements of your ring here scalars and elements of your module vectors. It's kind of standard terminology. This is the same thing as vector space in linear algebra, except over rings, and that will be on the next slide. And it's useful to consider these things in greater generality than linear algebra. I mean, this is still linear algebra, but it's in like high school linear algebra over any rings. Okay, so we have all of this data: addition, subtraction, zero, and scaling. And what we require for it to make any sense, otherwise we just have a bunch of random operations and functions, is the following properties. Again, we have the usual things about addition, the same way with rings. These properties about addition and zero and negative, additive inverse taking are called the properties of an abelian group. And this is what we need for ring. We always require an abelian group structure on addition, and for a module, we also require an abelian group structure on addition. But also here, we have the scaling, and what we require about scaling are the following four properties. We require that scaling by 1 does nothing, which makes sense. Scaling by 1 should do nothing. We also want kind of associativity of scaling, but it's not literally the associativity of binary operation, because the concatenation here, so I'm looking at the second from the top right point, lambda eta u is lambda eta u, reparenthesized. The concatenation between lambda and eta represents multiplication in our ring R. The concatenation between eta and u and lambda eta and u represents our scaling. And so we kind of want that it's compatible in this way. So multiplication in the ring should work well with the scaling. And we also want this distributivity. Again, it's not literally distributivity in the sense of operations, it's this distributivity with scaling. And once you have all of this, yes, we call M an R module. And again, yes, if we forget about R and only think about addition, zero, and additive inverse taking is called an abelian group, it's good to know. It's just terminology. If we forget about the commutativity assumption, we just get what's called a group. Okay, so first of all, every abelian group is a Z module. So if you forget about the four properties I put on the right here, we just have some set M plus 0 and minus, we can make that into a Z module by defining that, well, 0z is 0, 1z, 0x is, let's take some vector v in our abelian group. We want to define scaling in order for it to be a module of a z. So, of course, 0v has to be 0. We can prove that by distributivity and some properties of the scaling that we require here is the same thing as with doing this in rings. So 0v has to be 0, 1v has to be 1, 2v by distributivity has to be v plus v, because it's 1 plus 1v. And 3v, v plus v plus v. Also negative 1v, negative v. So there's only one choice of how we can make a scaling, and this scaling actually works. So abelian groups are the same thing as Z modules. So kind of, it might be interesting if you've learned about groups before, if you've learned about linear algebra. Essentially, abelian groups are no different than linear algebra over the integers. And this also illustrates that linear algebra over fields and linear algebra over the integers, say, or over abstract rings behaves very differently. Actually, yes, over fields, we call modules vector spaces. And I said, even if you're not a vector space with a module, you still call the elements vectors. And the theory is really a lot tamer, and we'll see some results later. I won't prove them, but I'll give them to you, of how much tamer the theory is over fields. And also, just quickly, let me mention here, just in the case of non-commutative rings, again, we're not doing that here, but just so you know the terminology, or at least the existence of the terminology, when we have a non-commutative ring, we have to differentiate between three types of modules: left, right, and bimodules. So bimodules are things which are and left and right modules. But we're not going to talk about that. Just a left module is essentially the same thing as a module, except you're doing a non-commutative ring, and the right thing as well. You have to differentiate because of non-commutative multiplication. Okay, so an example immediately we get is that any commutative ring can be made a module over itself, just scaling its multiplication. In that case, the properties before literally the same thing as for a ring. So yes, we have the rings modules. And immediately let me give also the product construction. It's the same thing as with rings, except now with modules over the same ring. If you have a bunch of modules over the same ring, we can take the product, and you do kind of the intuitive thing as earlier. You add and scale component-wise, and 0 is also all zeros, and additive inverse taking is also component-wise. And it's again a module. And this is a very useful way of constructing modules, and many modules come up this way. So immediately I want to give it here because then we'll be able to give some more examples later. Again, it's just kind of the usual construction. You can do this again in any category. I'm not going to talk about category theory here, but it's a toolkit of machinery that you can apply in many situations, and you get kind of these same notions we're seeing here. So you can think about this talk I'm giving here in the context of universal algebra, where all of these things are viewed as algebraic structures, or in the context of category theory, all of these things are viewed as objects of category. And then immediately you get many implications. You get trivial corollaries of universal algebra, you get trivial corollaries of category theory, things like that. So okay, here's an important family of examples. And what we can do, I think, that we can combine the previous two examples, take some commutative ring R and some index set I. We can just take the power of R to the I, because R is a module over itself. And then we can just multiply with itself for every index in I, and we can get this power. If I is a finite set of some Carnot, we can also just write R to the n. This is kind of the most common examples of modules that you see in high school linear algebra. So yes, just universal algebra. Okay, I'll be a little less thorough in going through the theory of modules, because that's just a bunch of linear algebra, and there's a lot to it actually, especially if you're not working with fields. So I'll just give the most important notions and immediately kind of I'll skip ahead through some of the theory. I'm not going to give you all of the relevant statements, but they're kind of, a lot of them are very intuitive. So for example, the same way that for a ring it suffices to give them addition and multiplication, for a module it suffices to give the addition and the scaling. The additive inverse taking is 0 and it's the only thing. And additive inverse taking is 0 follow from the addition to scaling. You don't have to specifically specify them. But claims like that, I'm not going to write them down. You can read about them in the linear algebra book. I just want to give you the main definitions of what is this about. What is this about? And for that, let's consider submodules. If you have some commutative ring R and a module over Rm, a subset n of m is a submodule. If the same way with subrings, we can make it a module for the structure on the module m. Namely, if it contains 0, it contains additive inverse of its elements, and it contains sums of its elements, and also multiples of its elements. Whenever this is true, we can view it as a module in its own right, and often we write like n less than equal to m if n is a submodule of m. And again, we can do the generation thing again. You can do generation in many contexts, and it's always very useful. So in this case, generation is sometimes referred to as span. If you have some module over commutative ring, you have module m over commutative ring R, and some arbitrary subset S of m, the submodule of m spanned by S, generated by S, is the smallest submodule of m containing S. And again, we have the same lemma with intersections. I'm not going to write them down. We can construct it as this intersection. And some notations are span of S, so these inner product brackets S. And just like with generating ideals, we can realize this as a set of all linear combinations of finite sequences of elements of S with coefficients in R. Those linear combinations are not multiplication, they're scaling. So an important notion here is that of linear independence. These linear combinations, we can think about them having, or like illustrating relationships between the elements we're taking linear combinations of. I'll give you an example to illustrate what I mean in a moment. But just for the definition, if you have some subset S of a module over a ring, a module M over a commutative ring R, it is called linearly independent, or R linearly independent to be more precise, if whenever we have some pairwise distinct S1 through Sn within it, and some elements lambda 1 through lambda n of R, if summing lambda I Si over I gives 0, then all of the lambdas are 0. And we do this, yeah, for any pairwise distinct S1 through Sn in S. Otherwise, they're called linear independent. So let's me give you an example. So both linear independence and dependence. So two vectors in R3. So R3, R is a field, so it's a ring, and a commutative ring. You can view it as a module over itself as a vector space because it's a field. And you can take its cube because it's a product of modules. So we have this vector space R3 over R. And we call it a real vector space because we're working over R. So often when you speak of modules, yeah, you speak of modules over a ring. R modules are over R. And often, generally, when you speak of things over a ring, you mean that the coefficients that you're considering when scaling and things like that are in this ring. So in R3, we have these two vectors, 1 to 3 and 0 to 8, and they are linearly independent. Why? Well, if you take a linear combination of them and it's 0, the factors have to be 0. It's just a question of linear algebra. You can do a computation, because the first coordinate is lambda 1. It's going to be 0 if the linear combination is 0, so lambda 1 is 0. But if lambda 1 is 0, lambda 2 is also 0, because 2 lambda 2 is 0. And 2 is not 0 because we're in R, characteristic 0. Again, characteristic 0, it doesn't matter. So geometrically, if you look at this, you can think of 1 to 3 and 0 to 8 as kind of arrows in three-dimensional space, or points in three-dimensional space. It's kind of better to think of them as arrows here. And when we take the span, we generate a plane into three-dimensional Euclidean space. And we visualize R3 as three-dimensional Euclidean space. I'm not going to go over how to do this, because it's pretty standard stuff, very important in physics and many other applications. You get a plane. And it makes sense. You start off with two vectors and you got something two-dimensional as plane. I'm not defining dimension just yet, but this is what you get. Now, if you start with linearly dependent vectors, for example, 1 to 3 and 2, 4, 6, well, 2 times 1 to 3 minus 2, 4, 6 is 0. Any multiple of a vector is linearly dependent with the vector, because precisely this reason, we can just, if you take alpha v, then alpha v times 1 alpha v minus alpha v is 0. So they're not linearly independent. So they're linearly dependent. We take these two vectors. When we represent them as arrows in three-dimensional space, they expand, but you only get a line, even though we start with two vectors. And this is kind of showing dependence. Actually, there are many contexts where you can get dependence also with other algebraic things, such as algebraic extensions. Speaking of algebraic dependence there, or also transcendental extensions, we'll mention that a little bit later, and also with graphs. In general, it's good to mention, it's a rare notion to come across, but it's actually very important in combinatorics. Also, funny enough, there's been some developments in algebraic geometry that have used this. I'm kind of going on a tangent here, but it's good to mention this notion of matroids. Matroids are an abstraction of the notion of dependence. Just let's be mentioned here. This is, if we take this notion of linear independence on some subset of a module, we get an example for matroid. So if you like matroids, this gives you a source of examples for matroids. So yes, we can think of linear independence of a finite subset of a module as the span of the subset being of the right size, so to say, the right dimension. But I'm not defining dimension. Actually, dimension is kind of tricky to define an arbitrary module. So a vector space, you have a very nice theory, and we'll get to why that is in a moment. But our arbitrary module of dimension might be kind of weird. So let's try talking about dimension. First, let's define the notion of a basis. A basis of a module of a commutative ring is a linearly independent subset which spans the whole module. And over vector spaces, we'll get that in a moment, there always exist bases. In any vector space of a field, there's always a basis. But over arbitrary modules, it's not true. This is kind of how more complicated the theory becomes once you drop the assumption of working over vector space, even just working over domains of a vector space. If you work with the integers, you get a billion groups. You have a billion groups which have no basis. It will be an example just in a moment. But if there does exist a basis, we call them modules free. And also something interesting, over vector spaces, if you have two bases of the same vector space over some field K, then they have the same amount of elements. This fails to be true over arbitrary modules. You might have a module, it is free, it has a basis, has multiple bases, and the multiple bases have different amounts of elements. But okay, if all the bases have the same amount of elements, we call this amount the rank of the module. And it's actually the same thing as the dimension. If it's a vector space, we call it the dimension. If it's a module, we call it the rank. There are many different notions of rank. It gets kind of messy because of the kind of atrocious things we consider, the modules without bases, etc. I mean, they're not atrocious, but they're atrocious if you try to think of them in terms of vector spaces and kind of canonical linear algebra over fields. So an example is actually a rich family of examples of free modules. In the sense, these are all the finite rank free modules. Are these? They're the modules Rn. So we take a commutative ring R, we take its nth power as a module of itself. And then we have this basis E1 through En. It's the same EI we used to prove that powers or products of more than one non-zero rings are not domains. EI is the element of Rn whose all coordinates are 0 except the ith, which is 1. This is a basis of Rn, and it shows that Rn is a free module over R. It's called the standard basis sometimes. So let's see a module without a basis. How horrible can it be? So we take the ring Z modulo to Z, and we only take it because we care about its abelian group structure. Every ring comes with an abelian group attached, and so we can view this as Z module, right? We have an element 0, the evens, 1, the odds, we can add them. And then we can scale them because we know that 2 times the odd should be odd plus odd. 3 times the odd should be odd plus odd plus odd. Negative 1 times the even should be negative even, etc. So we have the Z module. And it's not free. Why? Well, for it to be free, it would have to have a basis. Now, if the basis does not contain 1, well, it's as a subset of 0. But 0 is a submodule, so it's going to be, the span of the basis is going to be contained in the singleton. 0 is actually going to be equal to 0. So this doesn't work. Any basis has to contain the singleton 1. Any subset of a linearly independent set is linearly independent because, well, in our definition of linear independence, we were quantifying over pairwise distinct elements in our set. If we have pairwise distinct elements in our subset, we have pairwise distinct elements in our set containing the subset. So subsets of linearly independent sets are linearly independent. So it follows if Z modulo 2Z had a basis, this basis would have to contain 1. And the basis is linearly independent, so the singleton 1 would have to be linearly independent, but that's not true. The singleton 1 in Z modulo 2Z is linearly dependent over the integers. So we have to view this as a Z module. Why? Well, simply because 2 times 1 equals 0. So we scale 1 by a non-zero element, and we get 0. So it's linearly dependent. It's a very weird thing if you try to think about it as arrows in three-dimensional space. You scale something by 2, it becomes 0, so it's linearly dependent with itself. This is something that can happen over arbitrary modules. So we have to be careful. You can't really use all of the theory of linear algebra. Some of it you can. Really, mostly what you can use is just the terminology of linear algebra. It becomes useful to talk about various notions such as linear maps, which is what we're going to do in a moment. Namely here, a linear map between two R modules, M and N, for our commutative ring, is a function from M to N. And again, just like with rings, we're talking about the underlying sets. So function from the underlying set of M to the underlying set of N, such that it preserves all of the structure. Again, we have the same thing with the first isomorphism theorem. We can realize this as a compositions of projections, isomorphisms, inclusions. It's all the same. I'm not going to go that into much detail, but this is a motivation for why we would care about this. And we just want to preserve all of this structure. And just like with, so an isomorphism is in the bijective linear map, and just like with rings, it suffices to require that it preserves addition and scaling. Or with rings, it also have to require that 1 is preserved here, that 0 is preserved follows because we preserve addition. Okay, so a very important fact about free modules is this kind of characterization of free modules. Namely, if you have a commutative ring R and free module M over R, and some module N over R. So we have something free over Rm and some module N. If you have some basis of M, it's free, so there exists one, and we have a function from the basis to N. So let's think very concretely. We have some basis, let's say it's finite, B1 through Bn. And then we have some elements of our module N, A1 through An. Then there is going to be a unique R-linear map from M to N, which maps the basis Bi onto Ai in our N. So essentially, what I'm saying here, linear maps out of free modules are uniquely given as functions out of the basis. This is what it means to be free. Freeness is a more general condition, it makes sense in many contexts. And here, free modules are like this. Free groups are a different topic, but they're essentially also characterized like this. It's a notion of a left adjoint in category theory, but that doesn't matter. So that's a lemma. Maybe to illustrate what's happening here, let's consider a vector space, a field R, and then vector space R2 and R3. Well, over a field, all vector spaces are free. This is standard linear algebra. And so we know that R2, R3 are free. And also we know that we've seen that both Rn is always free for any commutative ring R. And so we can have the basis E1 and E2 of R2, 1, 0, and 0, 1. Now, let's say I want a linear map which maps E1 to 1 to 3 and E2 to 0, 0, 1 to E3 of R3. Well, such a linear map, it has to map xy, which is x E1 plus y E2, to x f of E1 plus y f of E2. Just because that's how linear maps work, they have to preserve, by the properties I wrote above, sums. So we get f of x E1 plus y E2 is f of x E1 plus f of y E2, and also scaling, so we can take x and y out. So, however, we know if f of E1 is 1 to 3 and f of E2 is 0, 0, 1, that x E1 plus y f E2 has to be x1 to 3 plus y 0, 0, 1. So xy has to map to x, 3x plus y. And in this way, we generally can construct and prove uniqueness of linear maps out of free modules. So I'm not going to go into too much detail here, but it's a very important property of free modules. It's called the universal property. Actually, later we're going to have something with polynomials, because polynomials are free algebras. We'll get to that in a moment. So something that we get as a corollary is that if you have two free modules of the same rank, so they both have bases of the same size, actually they don't have to have unique size of bases, but if they do, that's also good. But if you have two modules and bases of the same size, we can get linear maps from one to another, so modules of the same commutative ring, by mapping one basis onto the other base because they have same size, and vice versa. Then these linear maps are going to be inverse to each other, and so we'll have that the modules are isomorphic. Again, I'm not really writing this out too carefully, but you can check it using the universal property I gave above. We get that three modules with the same, with bases of the same size are isomorphic. But definitely we get over vector spaces, in which case here rank is called dimension, and all vector spaces are free. Vector spaces are just classified by the dimension. If you have two vector spaces over the same field and have the same dimension, well, they're isomorphic. And vice versa, to every dimension, you have a unique vector space over a field. So really, there isn't really any richness to the structure of vector spaces over a field. Actually, it's very interesting what one can do. One can measure the sort of richness of modules, especially a certain kind of modules called finitely generated projective modules over a commutative ring by a so-called K group. And this whole branch of study that has to do with that in linear algebra called K theory. I'm not going to get into that here, but it's just interesting to mention that kind of how wild the linear algebraic structure of modules can get over a commutative ring is actually something quantifiable by a specific group. As a novel algebraic structure. I'm not going. I mean, I defined what the group is earlier. Just this sort of thing, and you can study K groups of say algebraic commutative rings and study this module structure. And yes, over fields, when we have vector spaces, it's kind of trivial. Well, you just get bases for every vector space, and then you can talk about really linear algebra, and even in the case of fields, is mostly used as a tool, as a toolbox of terminology. I mean, sure, you have various theorems, but I feel like really you could say it's kind of a subjective statement that really the most important things in linear algebra are the notions they bring. You can view many things as vector spaces and modules, and then you can apply these notions, and then you have already this toolkit of theorems you have. I mean, it's kind of true about all branches of mathematics. I'm kind of making philosophical subjective statements here, so let's move on to the real math. So just as an example of linear independence and spanning, if you have a vector space, then given n linearly independent vectors, you're going to span a n-dimensional subspace of it, because all, well, that's kind of trivial. Okay, maybe it's a boring example, but just kind of to illustrate how terminology works, we have this. Okay, so another thing we can do with modules. Oh, yes, a question? Yes. So the question is whether okay, so we have to be assuming the axiom of choice. I mean, okay, so the question is this true for infinite dimensional vector spaces as well? And okay, depends what you mean by this. It is true that any two modules of the same rank are isomorphic. No matter you just map one base to another. This is fully constructive. You don't need the axiom of choice. It is not true without assuming the axiom of choice that every vector space over a field is free. So when I said that all vector spaces over a field is free, I'm using the modern CFC perspective on things. So if you take this perspective, then you can prove by Zorn's lemma that every vector space admits a basis, so hence it's free. Then you can also use some arguments about linear dependence over fields to show that the bases have the same amount of elements, they have a dimension. And then you've proven every vector space is free of some dimension, unique dimension, and then you get isomorphism from measuring the basis. It is true even for infinite dimensional things. You have to be careful, however. One misconception you could have is that Rn has dimension n. This is true if n is finite. If n is infinite, Rn becomes actually larger than n-dimensional. If I recall correctly, it's the dimension of the power set of n in infinite dimension. Maybe I'm misremembering, but you have to be careful. If you take, you want to take the direct sum instead of the product. That's the thing. But yes, this works also for infinite dimensional vector spaces. I mean, if I'm not saying that something is finite dimensional, then my claim here should be correct about infinite dimension as well, unless it's incorrect, in which case I made a mistake. But I don't think it is. It's a question of how much you trust me. And if you don't trust me, you can look this up in the linear algebra. Okay, I hope this answers the question. Okay. Yeah. So the question is the difference between the direct sum and the product. Again, taking direct sums is kind of like taking infinite products, but you make it tamer. You only consider finite combinations of things from your index strings or index vector spaces or modules. So if you want to get a vector space of dimension d over field k, you can take a direct sum of k with itself d times, d might be infinite here, and you're going to get something of dimension d. That's true. If you take the product, this is only going to work if d is finite. Otherwise, you get something of larger dimension. Okay, so I just not to confuse everybody, I've only defined direct sums of rings, but you can also take direct sums of modules. It's just defined analogously the same way I've defined direct products of modules. Just take all of the elements which are zero, which have the coordinate 0 everywhere except a finite set of indices. So if you want to get a vector space of some specific dimension, you want to direct sum your field with itself as a modulo of itself or vector space of itself that dimension amount of times. That's what you want to do. If you take the product, you get something larger and infinite dimension. But again, all of the claims here work also in infinite dimension. It's just that when you're constructing your rings, your modules that are infinite dimensional, your vector spaces, you want to be careful. You can't just take a power, you take a direct sum. So someone is mentioning the difference between the definition of basis for finite and infinite dimensional spaces, and I would disagree that it's different because you always want to take finite linear combinations. Well, okay, I guess you can view it as a more general. Okay, yeah, that's a good point. So yeah, so somebody's mentioning Schauder basis. It's a good thing to bring up, and I've seen that actually some analysts don't keep that in mind. But really, in algebra, just linear algebra without any analysis, the notion of Schauder basis does not exist, because to talk about Schauder basis, we need a topology, which we do not have here. Here we are just working with algebraic things. So of an arbitrary field, the notion of a Schauder basis doesn't even make sense. All of it, for that reason, I'm talking about basis in the algebraic sense. You can also consider the theory of Schauder basis, which is a different notion of basis, and then you think about convergent. So you, instead of taking the span of the basis, you kind of take the closed span. You get a different notion of basis, and it's more useful in analysis. And it is a different thing. And in that case, the theory I'm giving you here kind of breaks down somewhat. I mean, it's a question of analysis then. But that's a different notion of basis. It's not algebraic. Not what we're doing here. I mean, you can try to make it algebraic again, but it's what we're doing here is just kind of classical algebra. All of the bases are in the sense of Hamel bases, in the sense I've defined. And if you take my definitions, what you take works out. But yes, you can have also Schauder basis over topological fields, in which case you have a different theory somewhat. Okay, well, maybe we can talk about this later. It's an interesting topic. Let me move on to talk about, yes, quotients of modules. And actually, the theory for modules is somewhat easier than that with rings, because in rings, we had to separately define subrings and ideals. We could only quotient by ideals, but not by subrings. I mean, maybe you didn't notice because I'm going at a fast pace, but for example, 2z, the set of even integers, is not a subring of the integers. The integers possess no subrings, because every subring has to contain 1, by definition. And if a subring contains 1, if it is 1, and 1 plus 1, and 1 plus 1 plus 1, so it contains all of the integers, because also negatives of its elements. So there's only one subring of the integers itself. And you cannot quotient by subrings. You can quotient by ideals. Different notion. But with modules, it's the same thing. The role that ideals play for rings is played for modules by submodules. And you can just quotient by them the same way. You given a commutative ring R and module M over R and some submodule N of say a submodule N of M. I'm sorry, that's a typo. Then the quotient of M by N is basically the same construction we did with ideals, except now we're doing it with modules. We're saying that x is similar to y if x minus y is an n. So we're identifying n with 0. Again, that's the idea. We want to identify it with 0. Then always when you, I mean, properly, when you take quotients, you quotient by an equivalence relation. But what one often does instead is one quotients by some subthing, and when one quotients by some substructure or some subset, one identifies it with 0 in a sense. So in topological spaces, we quotient by a subset, we identify with a point. Here we identify with 0. So we want to identify an n with 0, and then by the same consideration, I mean, I could talk about congruences here again. The same theory applies. I just don't want to make this too long with modules. We can define this equivalence relation x similar to y whenever x minus y is an n, and then you take the quotient. And then the intuitive definition of scaling in addition gives you a modular structure of the quotient. And it works out just like that. An interesting thing to mark is actually when you view a commutative ring as a modulo itself, the submodules are precisely the ideals. If you just look at the definition of a submodule and definition of an ideal, characterization of an ideal I gave, the conditions are the same. You want that scaling is the scaling of an element of a submodule has to be the submodule. The same thing with an ideal, and the sum of two elements has to be 10, and 0 and additive inverses. That's the same thing for submodules. So are submodules of R the same thing as ideals of R? And then the quotient rings, when viewed as R modules, then the quotient rings can be viewed as R modules. That's something you can do. And it's the same thing as doing the quotient module. Yes, so that's an interesting observation to make, and it simplifies the theory a great deal. It's a very nice coincidence. Perhaps that's really the reason why linear algebra turns out to be so useful. So, okay, we have the same thing as with rings. We have the kernels and images of linear maps, and it's the same. The kernel is the preimage of 0. The image is the image, a set of all values. And again, these are submodules in this case. Earlier, it was also interesting. We had that the kernel wasn't something you could quotient by an ideal. It wasn't a subring. The image was a subring. Here, it's both a submodule because it's the same thing. In general, a kernel is going to be something you quotient by in the image a substructure. But in this case, it's just the same because ideals are submodules in this case. So if you have a linear map between some modules of a ring, commutative ring, then its kernel is defined as so and its image as well, and we get the first isomorphism theorem the same way. I mean, again, the first isomorphism theorem holds in a great deal of generality. We can see it in the context of universal algebra. So we get this. It's a useful theorem to know, similarly as with rings. Okay, so now let's talk about a related notion of commutative algebras, and it's kind of a strengthening of the notion of a module in the sense that we add more structure. Really, the notion of an algebra is when one takes the notion of a module and one imposes a multiplication. And when one does it, instead of writing out all of the conditions, one actually can just simplify the definition to the following. A commutative algebra over a commutative ring R, or commutative R algebra, is given by the data of a commutative ring and a homomorphism, so commutative ring A, and homomorphism from R to A. If we have that, well, we can multiply elements of A, we can add elements of A, and we can scale elements of A by elements of R by just taking the values of elements of R in this homomorphism and multiplying. This homomorphism is sometimes called the structure map. Generally, in these category theoretic and algebraic geometric circles, structure maps of things refer to the maps that are part of the definition. So, for example, the structure maps of a ring would be the addition, the multiplication, the additive inverse taking here. This is one of the structure maps. The structure maps, if you know some category theory, the structure maps of a product are the projections, not the projections as in of a quotient, but onto the coordinates. That's a different topic, but this is just a good terminology to know. And notice I'm saying commutative R algebra. I could again go to the non-commutative case, it just becomes much more messy. I don't want to do that. And sometimes in the non-commutative case, you cannot do this trick where you think of a ring homomorphism, or you have to go to the center of an algebra. Whatever that is, I'm not going to find that. Just let's stick to commutative case, it's easier here, and that's really all we need for algebraic geometry. So that's in the commutative R algebra. And again, it's a strengthening of a notion of a module in the sense that we've added more structure. Every commutative algebra is viewed as a module over the same ring, simply because we can define scaling as I've written above. We just apply the function, then the ring homomorphism, then we multiply. And you check because the ring homomorphism, all of the conditions are satisfied. It's exactly what being a ring homomorphism is requiring. Really, you could redefine a commutative R algebra by writing out properties on a module, not the properties, but more structure. You define a multiplication map on the module, but it just turns out to be this thing. So it's much easier to write this way. So the way that abelian groups are Z modules, actually, because every commutative ring, or just every ring admits a unique homomorphism from the integers, every commutative ring is in a unique way a commutative Z algebra. So commutative Z algebras are the same thing as commutative rings. And Z modules are the same thing as abelian groups. So it kind of, this is the fact that Z is the initial ring. And I don't know how the lectures will be looking at, are going to be covering this, but actually this does matter in algebraic geometry because in this way, well, okay, I won't say too much about algebraic geometry because I will go far afield, but this is a quite interesting observation that this actually matters quite a lot because often we do like to think about algebras in algebraic geometry, not just rings. So an algebra is kind of a relative ring. We have a ring, A, but we also have some ring that we can scale by. We have kind of some rings picked out, the coefficient rings, so to say, R is to say the coefficients of our algebra. So in a sense, a commutative R algebra, or just a commutative algebra, is some commutative ring A, and we've picked out a commutative subring in a sense. Not subring, but just some way of scaling. I mean, a subring also gives us an algebra structure by the inclusion. This will be an example. So if you have a commutative ring R and a subring R of S, then, sorry, commutative ring S and a subring R of S, then the inclusion makes S into commutative R algebra. So kind of, these are the, so say, faithful algebras. I don't think that's the correct terminology, but in a sense, this is what scaling works as you would want it to work. You don't have two different elements which scale the same. And we can also make quotients into our algebras. If you have our algebra S, we can quotient it by some ideal, and then by composing it with the projection, we get the homomorphism from our structure map, and we get a commutative algebra projection of the quotient. Okay, so now let's get to so this was the part of this section where I talk about some general linear algebraic things because they're just important to have and they're kind of relevant here. But now I'm going to I think this is the heart of my talk because I want to illustrate how all of these notions play into algebraic geometric terms and how we get the geometry of the rings to some extent. I mean, again, I'm not going to go into too much detail. That will be the whole of what the lectures are going to be about. But I just want to give you kind of the intuition of what is going to be happening in the abstract context, in the more classical context. And to go to a more classical context, we're going to look at some topological notions or analytical notions. Actually, the notions of scheme theory, which is the perspective in algebraic geometry that lectures are going to be taking, this is the modern notion, was heavily motivated by functional analysis. One of the key developers of the subject, Alexander Grothendieck, came as a functional analyst, and many of the notions of algebraic geometry, such as the spectrum, come from notions of functional analysis, such as the spectrum for functional analysis, the spectrum of a bounded operator, Gelfand duality. You don't have to know what this means. This is kind of a general remark. All I'm saying here is we are looking at this more classical situation to gain some intuition. So for that, let's fix some rational number n and some subset omega of Rn. We could also take, and also some p in omega. Okay, a lot of stuff, but just we have some shape. That's all we're doing. We're taking some shape. You could also take some topological space. And that's all we're doing. Okay, what we do next, we consider all of the continuous functions on omega that are real valued. So, okay, if you've never seen topology before, let me explain what I'm doing here. We've took some subset omega of Rn, and now we're considering some functions from omega to R, functions which satisfy some property. And this property basically says that if you want to control how close points in the values of a function, you can do this by controlling how close they are in the domain. The specific definition is written out below, is written kind of in standard. Oh, and the definition is written out incorrectly because the second inequality should be with a delta, not an epsilon. I'm sorry for that. But this is just standard analytical things. And again, you don't need to know topology to follow along what I'm going to say. Just if you're willing to take some things for granted, notion of a continuous function is kind of just a notion of a function that's well enough behaved for our purposes. It's kind of tame. And because sums and products of continuous functions are continuous, and additive inverses of continuous functions are continuous, and the constant function is 0 and 1 are continuous, we get that the ring, sorry, this should be a C omega, not CR. C omega is a subring of the ring of all functions from omega to R, of R to the omega. So we can view this collection of functions as a ring. And that's really the key insight. This is an insight that happened around the 60s of the 19th century by people like, oh, I don't remember the people. You can find this in Eisenbach's book, the history. It was this insight that we can think about geometric shapes as the rings of functions on them with some properties. And this is really the heart of algebraic geometry. We think of shapes as the functions on them. And we'll talk about this for this section. So we have this ring of functions on omega, and they are rings. So we consider these nice functions. We can add them, multiply them. We have 0 and 1. We can also, instead of C, take many other things. You can take CK, K times differential functions, if omega has some smooth differentiable structure. Or we can take holomorphic functions. That's very interesting for, again, what I was talking about earlier in response to the question about characteristics. So doing complex geometry, you can get a bridge within algebraic geometry and complex geometry. Instead of schemes, you have so-called analytic spaces. But again, I don't want to go too far afield. You can replace C with many things. Actually, later, the lectures will develop somewhat the sheaf formalism. Really, we just want a sheaf here. But don't worry about what the sheaf is. That's for later. This is just to motivate the notions. So we'll have to recall, however, even if you don't know any topology, it's important to know here that a subset of omega is called open if whenever I have a point in the subset, there's some buffer I can give you such that all the points of omega around that point in our subset of this buffer distance or closer than this buffer distance are contained in omega. So essentially, how you can think about openness is that all of the points of our set are kind of in the interior of the set. They have some room around them. Well, another way of thinking about it, this is computability theory perspective. You can think of a set is open if you can check that something is a okay, sorry. I want to make a remark here, but I don't think I'm familiar with computability theory enough to make this remark. Maybe I'll talk about this next week in my topology talk. I'll have to read up a little bit. This is another way, nice way of using open sets. Really, the geometric picture is what's more useful here. There's some buffer room around our point in the set. And just one more remark to kind of bring into perspective what we were doing earlier. This C omega, it's an R algebra, real algebra. Why? Because we can take the map from the real numbers to C omega, which maps every real number to the constant function of that value in omega. It's a ring homomorphism, you can check, which makes C omega into, oh, again, sorry, this should be C omega, not CR. C omega, it makes C omega into commutative real algebra. And this is kind of also where the algebra perspective, the relative perspective, comes into play later in algebraic geometry. Okay, but to know what this means, you have to know some algebraic geometry. But okay, here comes a very important notion, which looks like a mess of symbols, but it's actually very geometric and intuitive if you have the right intuition for it. Let's define this family of things, AP omega. So remember, P was some point in omega, we just pick some point. And what this is going to be, this is going to be the set of pairs of functions fu, such that f is a continuous function on u, real valued, and u is an open subset of omega containing p, some neighborhood around p. So essentially, elements of AP omega are functions, continuous functions defined in the neighborhood of p. We're kind of looking at things locally around p. And then we can define a binary relation tilde on AP omega, saying that fu is similar to gv, it's going to be an equivalence relation, whenever f and g agree to the intersection of u and v. And we can check that if we take the quotient, so this is tilde, p should be tilde, we can define addition and multiplication like so. We just add and multiply the functions and we consider the intersection. The intersection of two open sets is open, you can check that. And so this is well defined. I mean, to check this is well defined, you have to do some more stuff, but you can check this is well defined. And this actually gives the quotient AP omega modulo this tilde a ring structure and also a real algebra structure, because you still have the constant functions. And this ring, CP omega, is called the stalk of continuous functions on omega at p. And elements of it are called germs. So what's some intuition? Let me show you this picture. Here I've took omega equals r, and I've took 2 points, p equals 0 and p equals 1. And we have these two functions also. These are functions in C omega, and in particular we can restrict a function C omega to any function, a continuous function, open subset of C omega, some CU, where U is some open subset, open neighborhood of 1 or 0. And my two functions in C omega are these. First of all, I have the identity function, r to r, which just maps x to x, and I have this kind of dampened that identity function. I cut it off at 1, -1. You can write out the minimum of 1 and the maximum of x to -1. And I've drawn the graphs here. And we can interpret these functions as germs. Germs around 0 or germs around 1. As germs around 0, they're the same. Locally around 0, you can take some open set around 0, say the interval from -1 to 1. Just open again means that 0 is in the interior, so when you have some buffer room. Around 0, they agree. Around 1, even though they have the same value, they do not agree anywhere locally, because you always have that no matter how close to 1 you get, there's always some stuff on the right of 1 that distance away that has f disagree with g. So kind of germs, they capture the notion of functions locally. And the stalk is just the collection of all kind of these local function thingies. And now we can study this ring. Something that turns out is that, so before I tell you what turns out, I first have to define this notion that a unit of a ring is just an element of multiplicative inverse. And kind of trivially, a field is a commutative ring in which the units are precisely all the non-zero elements. Yeah, okay, so I was a little bit quick to tell you what's quick to tease you what's to come. There's some things I have to mention. We also have this important homomorphism. It goes from C omega to R, and it maps some function to its value at P. It's just evaluation, and you can check it's a homomorphism, basically the projection of the product, if you know what that means. And actually, this happens to induce a homomorphism from our stalk to R. Why? Because if two functions agree on the neighborhood of P, well, they agree at P as well. So then we can evaluate them at P, and it makes sense. This is well defined. We get a homomorphism. And something interesting to consider is the kernel of the homomorphism. And actually, what turns out is that the units of our stalk are precisely all of the germs which don't vanish at P. So everything which is outside of the kernel of the homomorphism. Well, why is it the case? If you have a germ of a function at P that does not vanish at P, because the function is continuous, locally around P is going to be non-zero, and you can write it, you can consider the function 1 over this function. And then this will give you a germ around P, and you can multiply them and get the germ 1. So you get that any function that's not 0 at p is a unit in the stock. Any germ that's not 0 at p is a unit. And of course, any unit in the stock is going to be non-zero at p, because if it's 0 at p, you cannot multiply by something to get something which is 1 at p, the constant function 1 in the stock. So we have this equality. And this kind of motivates the notion of a local ring, because local rings are rings that kind of model the situation that you get when you take the stock of a space. So for that, notice that by the first isomorphism theorem, the kernel of the evaluation map is the maximal ideal of CP omega of the stock. Why? Because the evaluation map is always surjective on the reals, because we can always consider the constant functions. We have the map, the structure map making the stock a real algebra is injective. So we can, for every real number, consider the continuous function which constantly takes on this value. And the evaluation at p of its germ at p is going to be this real number. Meaning that this map, the homomorphism fp, is surjective on the real numbers. Its image is the real numbers. And by the first isomorphism theorem, just reading it off, the quotient of the stock is isomorphic to real numbers. Now, this means that the quotient is a field, and hence this means that this kernel is a maximal ideal. But actually, something interesting that turns out, this kernel is the only maximal ideal of our stock. Why? If we take another ideal of our stock, and if it is not contained in the kernel, well, by our previous slide, we note that anything not in the kernel is a unit. So if our ideal is contained is not contained in the kernel of our evaluation map, it has an element outside of the kernel, so it contains a unit. Any ideal which contains a unit contains every element of our ring, because we can always write. So let's say we have some unit u in our ideal M. Then for every element in our stock x, we have that x is u times u inverse x. So it's a multiple of u. As a multiple of something in an ideal, it's in this ideal. So x is nm, which means that the stock is a subset of m, so m is all of the stock. So the only ideal which is not contained in the kernel is the whole ring. So if you want a maximal ideal, it cannot not equal this ideal. Always it is contained within it, but not equal to it, and also is contained in the whole ring. So you have 3 ideals above it at least. So it's not, the quotient is not a field. So all this is showing is that this is the only maximal ideal in our stock, this kernel. And this is what one defines as a local ring. A local ring is a ring which has a unique maximal ideal, a commutative ring usually. It depends on conventions. The definition makes sense for any ring, but we'll only consider commutative rings. And by the argument above, this is the same as requiring that the complement of some ideal is the unit. This ideal follows maximal because we take the quotient, and then we get that on the right-hand side we have r modulo m without m modulo m. So just r modulo m without 0, and we get that this is the unit of r modulo m. I mean, okay, this is not really a formal argument. This is kind of like the analysis proofs where you sum the differential and look at an infinite series, do a bunch of illegal things, write d over dx as d times dx to the power of -1. You can do this sort of argument here, do modulo p, and you see that if you identify m with 0, you get that the units of r modulo m are just the non-zero elements of r modulo m, so the quotient is a field, because the units are the non-zero elements. And it's also the unique maximal ideal, so that then m is a maximal ideal. It's unique by the above argument, because everything outside of m is a unit. And this is the definition of a local ring. And we've seen above that these stocks, they're local rings. And this is what the terminology comes from. I mean, you might have seen this in the algebra class and wondered why it's called local. The reason it's called local is because these rings arrive from stocks, and then the maximal ideals are all of the elements which evaluate at p to 0. So yes, CP omega is local, and it has a unique maximal ideal, the kernel. Now, something to note, which is interesting in this case, but it doesn't quite work out as one would wish. I mean, maybe you wouldn't wish this, but in algebraic geometry, there's something you can really do nicely here. Namely, so notice that elements of our stock can be written of the form f over g. I mean, you want to take some equivalence class, add some open neighborhood on p, but essentially you can write them as f over g, where f and g are continuous functions on the neighborhood of p, and g of p is not 0. Okay, it's kind of trivial. At least any such function is an element of the stock, and any element of the stock can be written this way. Maybe this sounds silly, but this is true. And so, in a sense, kind of, we can get all of the continuous functions in the stock this way. And, well, all of the elements of the stock, because the stock is by definition of continuous functions. So in a sense, we're forming the stalk by inverting all of the elements which don't lie in the kernel of the evaluation map. So G can be 0 outside of P. If G is 0 outside of P, we cannot take 1 over G on the whole of omega, because, well, we cannot divide 1 over 0. But if it's not 0 locally around P, then it's fine, and then you can invert it. So really, if we start with the ring CP omega, then if we invert all of the elements which are not 0 at P, which are outside this maximal ideal, we get our local ring, our stalk. And this is the process of localization. In general, we can do the following. Say that we have some commutative ring R and some multiplicative subset of R S. Well, a multiplicative subset of R is a subset S which contains 1 and contains any product of its two elements. Then if we have such a subset, we can localize our ring by it. If we just kind of formally take fractions, and fractions are going to be equivalent classes of ordered pairs, where we say that Fs, like F over S, is equivalent to G over T. And in our numerator, we have an arbitrary element of the ring. F is, or G are arbitrary. But in our denominator, what we're inverting is in our multiplicative system. And we say that these two pairs are equivalent to fraction if F times T minus G times S, and there's a technical detail here, times some element R of S is 0. Now we have to multiply here by some element R of S because we're not in the domain in general. In the domain, we can forget about this, but outside of the domain, you have things like 2 times 2 equals 0, where 2 is not 0, so this is kind of the thing you have to do. It's a technical thing. If you're in a domain, you don't have to worry about this. You can forget this, the R in S part. But in a general commutative ring, you have to add this. But this is essentially just saying that kind of F over S minus G over T equals 0 intuitively. And then we have these, we can check this in Equivalence Relation. It's something you have to check. It's kind of a straightforward exercise. And then we can define the ring structure on the localization on this set of all fractions, formal fractions, S inverse R. And we just do kind of the intuitive definition of how you want fractions to work. And you can check this is well defined and it gives you ring property, ring structure. This is how you can localize rings. Now, something we can do in general, kind of generalizing what happened above. Let's say you have some commutative ring R and some prime ideal P of R. P, like we can think of the example above as R we take C omega, and as P we take the kernel of the evaluation map. Actually, in that case, it's a maximal ideal. But we can just take some prime ideal. That's good enough. We take some prime ideal, then the complement of this prime ideal of a multiplicative system. Why? Well, because the ideal is prime, it's not all of R, so it doesn't contain 1. Because if it contained 1, it contains a unit, it would be the whole ring. And also, if it doesn't contain two elements, it doesn't contain the product. Because it's a prime ideal. That's what it means to be prime. If x and y are not 0, then xy is not 0 in the quotient by P. And this is precisely saying that the complement of P is a multiplicative system. And this is why we can invert formally also what happened above. We can take the complement of the kernel and just invert formally. I mean, above we are not formally inverting, I'll get to that in a second, but this is what you can do instead generally. You can generalize the above situation and just formally invert by inverting all the elements which are outside your prime ideal. And this is called the localization at the prime ideal, and it's simply written R underscore P. Instead of writing like R without P to the power of -1, people got tired of doing that, they just write R underscore P. So above, we can do the same thing. We can take RC omega and P the kernel, and then we have this localization. And it's kind of the formal fractions F over G, where G is not 0 at P. But it turns out that, well, we have a homomorphism. Any such formal fraction you can interpret as a function, but it's not injective. You can have different F and G, but you can have different how do I put this well? Well, there are some complications. Let me not go into this and mess this up, but you have some complications with doing this in this context. In algebraic geometry, you replace C with some over sheaf, some over notional functions, and you get a nicer structure here. But here you have to differentiate between the formal localization and the stalk. There's some subtle differences, I believe. We can talk about this later, maybe. Right now, not the key point is not coming to my mind, but there's some, I believe, subtle differences. But it's a very analogous situation otherwise. We have a homomorphism from the stalk, from the localization to the stalk. Okay, so just like we get the local ring type off, actually we get the local ring when we always localize the prime ideal. Well, the reason is because when we, I mean, okay, the reason is, well, what I wrote here as a proof is basically what I told you earlier with the quotient by P, and we've inverted all the elements outside of P, so the units are exactly everything outside of P. Of course, you have to check some things here, but that's the idea, essentially. So not all localizations, however, come from prime ideals, and you might have localizations which are not local. For example, take some commutative ring R and an element X. We can take all of the powers of X. It's going to be a multiplicative subsystem because we have one and we have any two elements of the form X to A and X to B. The product is F to A plus B, so it's also an element. So it's a multiplicative subset we can localize. And localization one also often knows the same subscript thing. I mean, it's kind of abuse notation because we've already used this for prime ideals, but we can do this. And if you localize the integers at 2, and okay, this is bad notation because Z2 written like this might also denote Z modulo 2Z and might also denote the two-adic integers. But there's three different things that in commutative algebra Z2 might denote. But in this case, it denotes localization, and what we get is the same thing as the adic integers. We've simply added 1/2 in a sense. And it's not local. We have 3 and 5 different maximal ideals. You can check that. So this is what you get. And this shows that you have also kind of non-geometric localizations in a way. So what can happen actually is that in this multiplicative system set of powers, you could have 0 actually. If you have an element X whose power is 0, if you don't have a domain, what can happen is an element is nilpotent, namely some power of it is 0. Because in a domain, if a power is 0, then if x to n is 0, then x times x to the n minus 1 is 0. So either x is 0 or x to n minus 1. And you keep going, then x is 0. If you're outside of a domain, like in matrices, you can have like this matrix, and it squares to 0. Then such elements are called nilpotent. And when you localize a nilpotent by a nilpotent element, you just get to 0 ring. It's boring. So you don't want to do that. Instead, what you have is that if you localize by a multiplicative system, or subset is the same thing, in a commutative ring, such that this subset doesn't contain 0 divisors, and what this means is that for every element of this subset and every element of the ring that's non-zero, the product is non-zero, then there's this canonical homomorphism from R to localization, mapping R to the fraction R over 1, and then it's injective. It's a thing you can check, it's kind of an exercise. Another important example of localization is when you take a domain and take the prime ideal 0. If you localize at 0, well, it's prime because the quotient by 0 is R, and R is a domain. If you localize at 0, you get a new ring, and actually it turns out this is a field. Again, kind of for the same reason as earlier, where you have the units are, you can check it's a field. And this field is known as the field of fractions. If you start with the integers, you get the rationals. So it's actually a very useful construction. You can do this with many domains, and often you might want to consider fields of fractions, and it has a specific geometric interpretation as well called birationality. So that would be everything, I think, about this kind of more geometric perspective on things. Maybe I didn't do it quite the justice it deserves, but I hope at least you saw the idea of how we want to achieve some geometric insight by looking at rings. We wish to look at rings of functions, and for example, one thing we can do, we can localize the point and try to understand the local behavior just by looking at the ring, by localizing formally. And this is one of the things that you can do in algebraic geometry. And because we have these concrete situations with like intuitive, like classical functions where this happens, we can try to abstract this away to arbitrary rings. And this is why I think it's really useful that I talk about this here, because later in lectures, we're going to do the same definitions kind of, but in an abstract context where you don't really have the same functions to look back on. This is somewhat of the intuition that you want to have. So next I'll talk about polynomials, but again, I think between these sections, it's good to ask if there are any questions. I mean, we were having some discussion. We can talk some more about this or any other questions. So any questions? No, no questions. Yep. No, I'll actually. So x. Oh, sorry. X should. I wanted to write x equals the matrix. That's a typo. So x is here the matrix. Um, so x is just the matrix 0, 1, 0, 0. I've not introduced polynomials yet. I'll talk about polynomials in a second. It's just an example where you have. Yep, exactly. Yeah, sorry. Yeah, I had to write all of these slides in 1 week, so I should have done a better job, but I have quite a few typos here. But yeah, this should be x equals this matrix. Okay. Any other questions? Okay, so I guess if there are no other questions, again, feel free to interrupt me during this section as well. This is now the last section. Let me come to the notion of polynomials. This is really very key in algebraic geometry, because what we do in algebraic geometry to achieve kind of a notion of continuous function, but instead of, we cannot talk about, we don't have a topology a priori. You can kind of get topology. I'll talk about it a little bit next week. We're thinking about polynomial functions, and that's a family of functions you get between powers of a ring, which are defined purely in algebraic means with the ring. So it's kind of a natural collection of functions. But actually, you have to be careful. Polynomials are not the same thing as functions. We'll get that in a moment. Just a priori, polynomials are sort of formal expressions of sorts. So what do I mean? If you have some commutative ring R, then the polynomial ring in one variable over R is, and one writes it kind of like this, R squared brackets X. And it's the same notation as with generating a subring, because if you view inside of this polynomial ring, it is generated by R and X. So it's kind of silly, but that's kind of where it's coming from. Or actually, a little bit the other way around. Actually, this notation came first, I believe, and then we have the generating notation. But what does ring consist of? And also, I want to mention, X here is just some formal variable. It could be anything. It's just a letter. It's just some symbol you use. It's just notational. This ring has such as elements, formal expressions of this kind. And what this means, so I write infinite sum from I equals 0 to infinity ai x to I. It's not really an infinite sum. It's just notation. And I also write a0 plus a1x plus a2x squared, etc. Again, it's just notation. There's no real addition happening at this point. It's just essentially a sequence of elements in R. So we have some zeroth coefficients, some first coefficients, a second coefficient, etc. That's one way of thinking about polynomials. It's not the most natural, if really nice thing you think about polynomials. We'll get to that in a moment. But this is kind of the easiest access point. What is a polynomial? Polynomial is just a formal expression. You just have a bunch of coefficients, at least in one variable. It's also called univariate. And then we can make this a ring. So we define addition multiplication like this. So we just add the coefficients. So like in the product ring, we just add the coefficients. But with multiplication, we do this sort of thing, which is what you would do if you were in a ring and X were an element that you don't know. And then you get these definitions, and this defines a ring. So important notion is that the degree of a polynomial is the largest power that appears. So we need to require that all but finally many of these coefficients are 0 to get the polynomial ring. Otherwise, we get what's known as the power series ring. It's still a ring. It just it's kind of like direct sums and direct products. If you don't require that all finally many are 0, we get a different thing which behaves slightly less nicer in a way. Actually, in a way, it doesn't behave much nicer, but it's nicer in the way of not giving us functions. This gives us functions. Power series don't give us functions because you cannot take infinite sums in arbitrary rings. So you can also, if you don't require that all but finally many of the coefficients are 0, you get the so-called formal power series ring in one variable. You can also extend this multiple variables. You get that in a moment. And it's noted like this. You can do like double brackets, or something people do like mathbb square brackets. That's another ring you get. So just some examples to make clear we're all on the same page. We can take as our ring R the rational numbers, and we take this polynomial ring, the univariate one in the variable x, and we have, for example, x squared plus 1 and x cubed minus x in it. In x squared is an element. We have the coefficient 0, 0, 1, 0, etc. And 1 is an element. 1, 0, 0, etc. We can add them and so on. This is the sort of well-definedness thing. You would like to check that for example, you would like to check that the sum of 1 and x is the same thing as 1 plus x, and I mean, that's just by definition straightforward. You can read it off. These things work out as you would like to do, as you would like them to do. It's just polynomials, something very common mathematics, so it behaves quite nicely. So we can do various calculations in this polynomial ring. It's a ring, and its elements are this. So we kind of, if we think of a ring as a generalized number system, here we're saying we think of numbers as these expressions. You can also imagine that we have some unknown number x, and we are doing formal manipulations with this. This is just intuition, but that's how you can think about it. So some useful facts. If we take a polynomial ring over a domain, it's a domain again. If you take it over a field, it's a PID, it's a principal ideal domain. So just like with the integers, every ideal is generated by a unique element. Not a unique element, but by a singleton, sorry. The generation is not unique, it's just that we can generate by a single element. So actually, it's very interesting to consider ideals in polynomial rings. This is where the geometry comes in. Later, we'll be considering a lot of ideals in polynomial rings. So we can also do multiple variables, and you can do it in many ways, but again, a very accessible way with what we're doing is just say that in 0 variables, we just get the ring back. It's kind of silly, but we can do that, I guess. And then if we have a polynomial ring in unvariables over some commutative ring R, in n plus 1, it's just the polynomial ring in one variable over the one in n variables. and we name the variables differently, again, just some formal names. And this way we can get multivariate polynomial rings. For example, again, so we're on the same page, in zxy, we've just added to zx, formerly y, and then we can do polynomials whose coefficients are in zx, and we've added a y, so for example, we do 2x plus 3, x plus 7, plus x plus n, y plus 8y squared, and you can do various computations, and we can rewrite it like this. You have the usual calculation rules as you wish. You get everything you want. And because we are taking formal combinations, two polynomials are the same when you write them out as sums of powers and products of variables whenever the coefficients are the same. So x minus y is not x plus y because negative 1 is 1 because you need the integers. So we can view these as our algebras. We have this map which just maps a element of our ring to the constant polynomial with the value, in the sense that it's just the zero of coefficients is r and everything else is 0. This is a ring homomorphism you can check, and it makes it in the commutative algebra. Something we can do with polynomials, which is getting closer to what we would like to mimic above, is we can evaluate them at elements of our ring if they're univariate. And this is why we cannot do this with power series. And also, I'm not going to talk about power series much more, but you can also do multivariate power series the same way I did with polynomial rings, just recursively. If you have a commutative ring R and some element P of R, and some polynomial f of R, we can define this value of f at P as just kind of formally inserting P into f and then interpreting this in our ring. So we just kind of, if you have the polynomial 2 plus 7x, we in the integers, also over the integers, and we evaluate the 2, we just plug 2 for x, and we get the number. I mean, it's just substitution in a sense. So we get this homomorphism from Rx to R. And so something very useful that turns out is that in any commutative ring, if you have some univariate polynomial, if it has a root, then it can be written as x minus b to some polynomial g. This k should be an r, sorry. So this is kind of a nice way of relating the function structure of polynomial. So you can think of univariate polynomials as functions this way to algebraic properties of the polynomials in the ring. And you have to be careful because actually, I don't know if we'll get to that. Okay, you have to be careful for a reason I'll say on the next slide. But for now, I want to mention, because we have this property that if f has a root p, then f is x minus b times g. And because we can check the degrees of polynomials over a domain, so we need a domain here because otherwise we get non-zero coefficients multiplied to 0, the degree is kind of a homomorphism in this way, in the sense that it maps products to sums. You get that any univariate polynomial over domain has only finitely many roots, because for every root it has, its degree has to be 1. So if it has n roots, you can write it first as x minus the first root times some polynomial, then the second polynomial has to have the other roots because it's a domain, and then you keep doing that, and then you get that f's degree is at least the amount of its roots. And if it had infinitely many roots, it would have infinite degree, which is impossible because we've assumed that they're all finitely many, all but finitely many of the coefficients are 0. So that's the thing we get. And you can also evaluate in higher amounts of variable, which is evaluate one after another. We can first plug in Pn for xn, and then Pn minus 1 for xn minus 1, etc. And we get, again, a function, in a sense, from Rn to R. You can do things this way, and I'll get to that in a moment as well. Get a homomorphism again. So yes, we can consider the map P to Fp, which to every polynomial in n variables of commutative ring R associates a function Rn to R. The functions are right called polynomial functions. This is our family of functions. If considering continuous functions, we consider these polynomial functions. And we can do this over any ring. So we're generalizing the situation to purely algebraic setting. I mean, this is kind of what you can do, just abstracting away the analysis to an algebraic setting. Right. So yes, this is the thing you have to be careful about. We have the two polynomials x and s squared in z modulo 2zx. So over this field, it's called F2 because it has two elements. This whole theory of finite fields, I said, but over this ring is z modulo 2z. And if you think of them as functions z modulo 2z, 2z modulo 2z, they're the same. If you plug in 0, you get 0. If you plug in 1, you get 1. There's no other elements to plug in. So despite being different polynomials, you get the same function. So you have to be careful. The really polynomials are different in functions. You have various relations between the notions, but it's different. But actually, it's only different in finite rings. So even though you have to be careful, for most cases it's fine. If you have an infinite ring, because any univariate polynomial has finding many roots, you can prove that even for multivariate polynomials, if they induce the same function, then they are the same as polynomials. So it's a very good fact to know. It's also quite useful. So this is why infinitude of rings is important, but also about fields. An important notion about polynomials over fields is that of algebraic closure. So a field is algebraically closed if every polynomial over it in one variable of positive degree has a root. So how to think about this notion? The real numbers aren't algebraically closed because c x squared plus 1 has no root, because x squared is also negative for real number x. But c is algebraically closed. So it's kind of a good way of, if you have an algebraically closed field, you in a sense understand all the polynomials because you can factor them into x minus a times x minus b times x minus c, etc. The a, b, c are roots, and then you multiply maybe by some unit, so by some non-zero complex number, or zero if you have a zero polynomial. So really, over algebraically closed fields, you can have a very simple univariate polynomial structure. That can be very useful in algebraic geometry, and that's for that reason, often in algebraic geometry, especially in classical algebraic geometry, you start working over algebraically closed fields. So historically, the very first algebraic geometry people ever did was over the real numbers, because that's kind of the most intuitive setting, and then they went to the complex numbers. And there's also another parallel development when they went from affine to projective space, but I'm not going to talk about that here, it will be in the lectures. So a good thing to know, hence, is that we can always, given a field K, up to isomorphism uniquely embedded into an algebraically closed field, such that this embedding has a nice property that every element of the algebraically closed field is a root of a polynomial in the embedded subfield in one variable. And this property of subfields of fields is called algebraicity, and you get this notion of an algebraic extension. So a field extension is just a field containing another field, and it's called algebraic if every element of the larger field is a root of a polynomial in the smaller field. So algebraic, being algebraically closed is kind of being maximal with respect to this ordering of algebraic extensions. Okay, this is again, just like with linear algebra, there's a lot that goes into here. There's this whole subject of field theory. Really, we don't need to go into this too much. I mean, it's useful to know. I think for lectures, we won't need too much field theory. What's important to know here is that every field has its algebraic closure, which is a unique algebraically closed field that it embeds to, again, up to isomorphism. We don't really differentiate isomorphic things because they're the same up to renaming the elements. Okay, so one thing about polynomial rings is that they are kind of free R algebras. This is that free, the Rn is a free R module. And formally, it's you can again state the universal property. With that, I first need to define what a R algebra homomorphism is. And with that, say we have some commutative ring R and some commutative R algebras A and B. Then an R algebra homomorphism from A to B is a ring homomorphism which just commutes with the scaling. So formally, you want scaling. The scaling is defined by the structure map, so you want it to work with the structure maps well. It's basically what you would think it is. You want it to work well with the scaling. And now we can state the statement of freeness that the commutative R algebra is free if, well, we have this property, but actually let's just state it for the polynomial range because we know that they are free, at least using this theorem. So say we have some commutative R algebra A and some elements A1 through AN of A, then there's a unique R algebra homomorphism from the polynomial ring in n variables over R to A, sending xi to AI for all I. So in this way, just the same way how linear maps out of three modules are defined on the base, determined by values on the basis, R algebra homomorphisms out of polynomial rings are determined by values on the variables. In a sense, this is justifying that we can think of polynomial rings as extending our base ring by some unknown elements, because these elements are just kind of, they could be anything, we can map them anywhere. There are no so-called relations between them, we know. So this actually is a very useful thing, this fact of freeness, because this allows us to say express the complex numbers as a quotient of the polynomial ring in one variable about reals. Namely, let's consider the map from the polynomial ring about real numbers to the complex numbers, mapping the variable to I. But you can check it's surjective because a plus bx maps to a plus bi, and for a and b real numbers, which is every complex number for some a and b. So it's a surjective map. So by the first isomorphism theorem, if you compute its kernel, which happens to be the ideal generated by x plus 1, we get that this quotient is the complex numbers. So in a sense, what we're doing here, we are adjoining the real numbers, some element x that we know nothing about, and then we are imposing. We know that x plus 1 is 0. This you can generate many examples of rings and actually R algebras this way. And you can actually later interpret them geometrically in algebraic geometry. So something else we can do this. We can quotient by the ideal algebra by x squared. And then we've essentially adjoined some element x, let's call it instead epsilon. So once we are in the quotient set, and we know that epsilon squared is 0. Why? Because x squared is 0 in the quotient rate, because x squared lies in the ideal of the quotient nearby. These are known as the dual numbers. And you can do many constructions this way, and you can all interpret them geometrically. Okay, the amount of variables you have. Remember, polynomials in n variables of a ring R give you functions Rn to R. So if you are in n variables, you're kind of in dimension n. So if you're in one variable, you're in one dimension. So it's not that geometric. There are some geometric ramifications, but more interesting is to look at more variables. So here's an example. We can take the polynomial ring in two variables, quotient by x y minus 1. So you're saying we're extending our ring with some unknown x and y, and we are saying that x is a multiplicative inverse to y. What we get is the same thing as if we localize our x at x. We kind of formally invert it. So you can do this, and this is also a geometric way of viewing it. In a sense, this is a statement that you can project a hyperbola y equals 1 over x onto the x-axis and get everything but to 0. I'm not going to explain why, but this is the geometric ways of interpreting these statements. So now that we've talked about some basic things about polynomials, one last thing I'd like to talk about in this talk is the notion of reducibility, which happens to be very useful for various technical computations for polynomials. I'm not sure if we will be doing many of those, but if you want to get your hands down on the polynomials, you really want to think about this notion. And it's motivated by asking when an element of a commutative ring generates a prime ideal. So which principal ideals are prime? And such elements are known as prime. Or sometimes you also require the elements non-zero, but it's kind of silly to do. It's just a bad historical convention. And in polynomial rings, there's this related notion that makes sense in every ring, that of a irreducible element, which happens to agree with prime elements. Irreducible elements are much nicer behaved, or much easier to understand in a sense. So an element of commutative ring R is irreducible if it's non-zero and not a unit. So not a unit has no multiplicative inverse. And whenever we write it as a product, one of the factors is a unit. So we cannot write it as a non-trivial product. And it happens that in polynomial rings, it happens that irreducible elements are the same thing as prime elements. And that's a fact in a more general family of rings, which we'll get in a second. But first, let me mention that because a polynomial has a root whenever root p, whenever x minus p times g for some polynomial g is this polynomial, if you have a polynomial of degree 2 or 3 in one variable or a domain, then it is irreducible whenever it has no roots. So for example, we know that x plus 1 is irreducible because it has no roots. If you had a root a, then x minus a, so actually, no, the way around. If we could write it as a product g times h, because we know how degrees work, either g is degree 2 and h is degree 0, or g is degree 1, h is degree 1, or g is degree 0, h is degree 2. If the degree is 0, then it's a constant, then it's invertible, so we can forget about 0 because our product is not 0 when we're in the domain. So we only care about the case of 2 degree 1 polynomials. But if we can write it as a degree 1 polynomial by an over degree 1 polynomial, we know that it has a root. So we're done. Actually, I guess we don't need the fact that we're not using the converse if it has a root and x minus p divides it. We're just saying that if x minus pi divides it, then we have a root. So we know that this is irreducible. This fails in higher degrees, of course. If you take the square of this, then it has no roots, but it's reducible. It's reducible. So the family of rings which have this property of prime elements, the same thing as reducible elements, are called unique factorization domains. And what defines them is that every non-zero element can be uniquely written as a product of irreducible elements up to multiplication by units. So units are again elements with multiplicative inverses. In polynomial rings, they are over a field the non-zero constant polynomials. And whenever we can write each element uniquely as a product of some irreducible polynomials, where the uniqueness is only up to replacing these irreducible polynomials by unit multiples of them, then we call it a unique factorization domain, a UFD. And it happens that in a unique factorization domain, prime and irreducible elements are the same, which is quite nice to know and we can use here. We know that this theorem over any field, a polynomial ring in any amount of variables is a unique factorization domain. And also more generally, if you have a unique domain, the polynomial ring over it in any amount of finite variables is also, and also principal ideal domains and unique factorization domains. So actually, the later remarks showed the first one. Okay, so there's this one nice criteria for checking reducibility called Eisenstein's criteria, and it's as following. It might look kind of intimidating at first, but actually it's very easy to apply and very useful in many situations. So let's say you have some domain R and a univariate polynomial, and okay, again, univariate things are in dimension 1 when things about them geometrically. So in algebraic geometry, we would like to apply criteria for reducibility in multiple variables, but remember that a polynomial ring in 3 variables is just a polynomial ring in 1 variable over the polynomial ring in 2 variables. So actually we can use this criteria in any amount of variables, we just have to single out a variable which we pick as like the last one. So let's say we have some polynomial over a domain, and let's say that the coefficients are without non-unit common divisors. This means as much that if we can write fi as a multiple of d for some element d of r for every I, then d is a unit. If this is true, such polynomials are known as primitive polynomials, and if also there's some prime ideal of r which contains the first n-1 coefficients, not the leading coefficient, not the coefficient of the highest power, so n is here the degree, and yeah, I should say actually fn is supposed to be not 0, I'm sorry, that should be mentioned here, because we just want it to be of degree n. I guess it follows if we have this not ideal p, so I guess you don't have to require it, but it'd be nice to write down. And also, if the ideal generated by the squares of the elements of P doesn't contain F0, then F is irreducible. Okay, there's a bunch of conditions. Let me illustrate an example. So let's take the polynomial ring in 2 variables over Q and consider 3x³ plus 2y. We want to show it's irreducible, so we can apply Eisenstein's criterion. So first we realize this polynomial ring as the polynomial ring in X over the polynomial ring in Y over Q. So now we need some prime ideal P. So actually, first we have to check that the coefficients here of y are without, oh sorry, of x are without non-unit common divisors. Well, the coefficients of x are 3 and 2y, because we have 2y in front of x to 0. And there are no non-unit divisors of 3 and 2y, because 3 is because that's how degrees work, and we are in qy. So okay, this polynomial is primitive in x. We've checked that. And now we need to find a prime ideal such that the coefficients, all of the coefficients with the leading term, so all of the 3 are in this prime ideal, 3 is not, and so we want that 2y is in this prime ideal, 3 is not in this prime ideal, and 2y is not the square of the prime ideal in the sense of the prime ideal generated by the squares. Well, we can just take the prime ideal generated by y, it's prime because the quotient of qy by y, we set y to 0, just get q, it's a field, so it's even the maximal ideal, not only prime, and the square is just 1 generated by y squared. So now we have that 2y is in the ideal generated by y. Yes, 3 is not in the ideal generated by y. That's also true because of degrees. 2y is not the ideal generated by y squared. That's also true, also by degrees. And so we've checked that f is reducible. Okay, that, that was quite the talk because of the length, because it's very good. I think it's, I mean, I hope it was a fairly helpful talk regarding algebra if you've not seen these things before. I mean, we'll need a lot of these things. So especially, so section 3 was kind of just a perspective on algebraic geometry. It's helpful, I hope. What you really need is, you definitely need to be familiar with polynomial things, section 4. I mean, maybe not the reducibility, but at least what a polynomial is. You need to be comfortable with saying, let k be a polynomial, like take k x1, x2, polynomial ring into variables. Some basic things about ideals is very important. Section 2 is very important. And well, section 1 is just the basics. So really, if you want to go with this again, I would advise look at sections 1, 2, and 4. You can skip 3. 3 is just kind of intuition. Maybe it'll be helpful further down the line. Also, let me recommend some books in commutative algebra. I've already mentioned the first one for some historical comments. It's Eisenbach's book, Commutative Algebra with a View Towards Algebraic Geometry. And also just the standard reference that people often use. It's Italian MacDonald Introduction to Commutative Algebra. Okay, so before we end this 4-hour-long talk, any questions about any of the talk? It doesn't have to be section 4. Okay, so someone is asking for exercises and problems. Yes, there are. I've mentioned some. I've omitted some proofs in this talk, and actually, I think they make good exercises. And I can also, you can find many exercises in the books that are written here. So, for example, I remember exercises in chapter 1 of Time McDonald very nice to do, and for algebraic geometry also chapter 1 of Eisenbud. Also, you can skip around in Eisenbud. Some of the later chapters have some localization stuff, etc. You can look at that. So you can do the exercises in the Stalk, like the omitted proofs mostly, and you can look at exercises in these two books. Or I will write the document with some exercises if you want. Okay. Anything else? So thank you everybody for coming. I mean, I appreciate that you gave me like 3.5 hours of your time to give you a mediocre talk about algebra. Uh, I mean, it's good enough that people care about algebra. Okay, I'm glad people like this. So yeah, let's hope the recording turned out well.